company, and that's why we really wanted to make this a community-driven event, where we ask for feedback. We include all good community people here. We include many people from the community to give the advice, give the suggestions, and give the decision power also to decide how the conference is run and who are the speakers, which was not very easy task. And we were very happy to receive the feedback from the very first emails that I sent out, asking, for example, Andreas and Will to join this effort. I was very surprised. Well, not very surprised, but I was very happy to receive the feedback that, yes, this is something that we really need for this community. So we're pretty excited now to open the first full scientific day to see what we have to offer to you today. But before that, I, of course, would like to thank all of you. We have 280 participants from many different countries, and it's wonderful to see that when we open this conference series like this, in the opening, actually, we couldn't even fit everybody into the conference. And we're very sorry that we couldn't give everybody who wanted to talk here, not even a poster, which was really a shame. We would have wanted to, of course, give everybody the opportunity to present their results. But we did put this then, for those who would not participate here on site, we have the online option, and I think this will kind of multiply our numbers in total. And so thanks for making this conference real. The conference is really you, the participants. Without you, there would be no conference. But of course, then the scientific committee deserves a big thank you, because the committee gave very good input basically on the program, how to organize it, how to make it convenient for you, what are the topics that we are going to discuss here, and of course, making the decision on the speakers. But it was not, the speaker decisions were not, again, dictated only by the scientific committee, but actually we had a very broad spectrum of scientific advisors. And how it worked is that the scientific advisors gave the committee suggestions on the speakers, and based on those suggestions, then the committee made the decision. They evaluated it in the scientific rounds, and we tried to put the most interesting science here on display. So thanks for the scientific advisors. This was very important input. And okay, actually, now I realize that these slides are not showing. Okay. I was just watching the screen here, so. So anyways, here I wanted to thank you and the scientific committee. Now we see also the faces of the committee, and here you can see the names of the scientific advisors, which is a long list. And then the organizing committee, obviously, and the other organizing members, they made a big job. And without them, my life would have been hell for the past 2 months. But thanks for your work. Everything has worked so far very smoothly. But of course, for the continuation of this event, it's extremely important that we have also the supporters. So big thank you to all of these companies that were financially supporting the event. We also hope to get your support in the next event. And of course, IQM, thanks to IQM board management, all IQMers, because they were supporting all the way, even initiating this idea of setting up the conference. So the scientific agenda for this day 2, we are starting with quantum error correction, which is, of course, one of the very hot topics in the community now. Many think that it's a way to general purpose useful quantum computers, and now we will see the latest sort of developments, where we are and where we are maybe going in the next couple of years. And then, as I said, we don't only want to focus on quantum computers, so we also think some other applications, non-computing applications for superconducting qubits is very important, and that's why we have this session then following. And although transmon qubits are great, we also think that the world needs new types of qubits, or it's really to have like leaps in fidelity and qubit numbers perhaps. We want to also have a session on unconventional qubits, so you will hear about very nice results from Fluxonium qubits, for example. And then we had actually quite many nice contributions from IQM, and then we decided that, okay, we could actually have kind of an IQM session at the end. It's not very long, but there's some good scientific results also from IQM at the end. So, with these words, I think I will still hand over to Stefan to say a few words about the practical announcements.
Exactly. So you probably have all been wondering what those stickers on your badge mean. If not, you're probably wondering now. So actually, to have less stress at the buffet at lunch, we decided to divide the lunch slot into 2 slots. So there is this lunch slot 1, which is starting at 12:30 and is like roughly 45 minutes. And then there's lunch slot 2, which starts at 1:15 and is also roughly 45 minutes. This is just to like have less stress at the buffet, and it would be great if you could try to stick to that schedule. And then, of course, this reminder on the back of your badge, you find not only the map, but also the Wi-Fi password. So all the important things are right close to your heart. And then there's one last thing. So the lunch will be, if you go out this room to the left, there you can find a restaurant, and there lunch will be served. And then for all people who will have a poster today, we kindly ask you to bring your posters 15 minutes before the session to put them up and be then there around your poster. So this will also be in this room. So you're kind of wondering how that works, but we'll remove the chairs and it'll look differently. And then we'll have the poster session in here. And now it's an honor to welcome on stage Will Oliver, who is chairing the next session on quantum error correction and mitigation. Welcome, Will.
Yeah, thank you very much for that. It's a pleasure to be here, and I'm pleased to chair this first session on quantum error correction and mitigation. If we want to realize the promise of quantum computing, we have many challenges ahead, but probably first and foremost is to make better qubits, and there are many ways to do that by mitigating the errors and, of course, by the holy grail of quantum error correction. And so with that, it's really a pleasure for me to welcome Professor Andreas Wallraff, who is one of the leaders of the field from the very beginning, but quite recently, and as we'll hear about today, he and his group have demonstrated a prototype quantum error correction scheme. And so with that, let me welcome Andreas Wallraff.
Okay, so thank you very much, Will, for the kind introduction. Thank you very much also for the scientific committee to invite us here to present our work. As Mikko said, it's a great opportunity first after this long time of COVID to see everyone here. And it's also, of course, a great opportunity to have this Superconducting Circuits conference, which we were really missing. And I was one of the ones that pointed out to Mikko, yes, that's a timely thing to do. Probably we should have done it 10 years ago. And so now someone stepped up and said, yes, okay, let's organize it. Because it's a lot of work to get these meetings to go, but I think it's for large benefit for the whole community. And I think even though it's only like half an evening last night that has passed, I think everyone has enjoyed it already as far as I could tell. Okay, so as Will mentioned, I'll talk about quantum error correction. And so on this slide here, you see a chip that we've made for this purpose. You see it from its front side, not from the back side. And so you see 17 superconducting qubits, 9 of which are used to store quantum information in a logical qubit, and 8 additional ones are used for detecting the errors in that logical qubit. And I'll explain how that works. So this work was done, the experimental part of it was done at ETH Zurich. The experimental team is listed here in the beginning. We've collaborated with Alexandre Blais and his team at the University of Sherbrooke, and also with Markus Müller at RWTH Aachen. And we also benefited from the interaction with the technical team at ETH. So I should also point out this was really a long-term team effort for a large experimental team at our lab at ETH. We started this more than 6 years ago as a part of the IARPA Logical Qubits program. And so a few of the people who've worked on the experiment are here. So there's Graham Norris, who's here and has a poster, and also Ans Rem, who's here and has a poster that I invite you to look at. There's also Christian Kraklund Andersen, who was one of the postdocs in our team working on error correction, and we had a nice paper on error detection a couple of years ago, who contributed to the beginnings of this project. And the lead authors for this work were Sebastian Krinner, a postdoc in our lab, and Nathan Lacroix, a graduate student. And so we have been at ETH Zurich now since more than 15 years, and all this would not have been possible without the efforts that everyone in our lab has made. And so on this list you see sort of everyone from our team who had a paper in our lab, and so what they're doing now. And it's kind of nice to see that there's quite a few faculty members from our lab around, and there's also a few of them are at IQM, at other quantum startups, and obviously I'm indebted to the great collaborations with other labs at ETH and with international collaborators. Good, so yesterday you've heard by Pedran about all the nice work that you can do in this NISQ domain with superconducting circuits. And there's been really an amazing set of results that has been achieved by many contributors in the field. I think Pedran and the team at Google have really played a leading role in exploring what is possible on this 50 qubit scale devices. But as you've seen, the work on these NISQ algorithms is really limited by errors occurring, by the decoherence rates that we currently observe. And in the end, we're not able to really execute deep quantum circuits with say, many hundreds or maybe in the future, many thousands of gates sequentially without really dealing with the errors, both the errors that are induced by decoherence in the devices, but also the control errors. And so I think it was clear to everyone from the beginning that quantum error correction would play an important role in the whole effort of building fault-tolerant quantum computers. But since quantum error correction is a very difficult task, and you mostly use your 20 or 50 qubits that you have to then make a single logical qubit, for a time there was really a focus, what could you do with 50 qubits to sort of look at potential interesting applications. And now that some of these have been explored, I think the focus comes back at the real goal, which is building a fault-tolerant universal quantum information processor, which will not happen without error correction. Good, so what is the challenge in error correction? So I think we're used to use error correction in all sorts of communication and computation settings. And recently at a school about quantum error correction, I learned that while we're not aware of it, many error correction schemes really get used in today's computation and more so in communication settings. So lots of error correction schemes are used, for example, when your cell phone communicates to the base station on some tower, and it's essential for increasing data rates and reliability in communication processes. And so therefore, error correction has kind of a long history in its development, also on the classical end. And as long as information is represented digitally, you essentially need to protect that information from errors, essentially looking at zeros changing into ones and ones changing into zeros. And in the quantum context, you would call those errors bit flips. But in quantum computers or in quantum devices, superposition states play a role. And these superposition states can also change. For example, a 0+1 state can turn into a 0-1 state, and that you would call a phase flip. So one of the challenges in quantum error correction is that you need to deal with these two types of errors, bit flips and phase flip errors. A second challenge is that typically in classical error correction, you would essentially look at the data that is stored and try to analyze it to notice whether an error occurred or not. And in quantum systems, this is harder to do because you can't just measure a superposition state and see whether it's still maintained or not, because that measurement would alter the superposition state, collapse it into one of its computational basis states. So you need to devise schemes that are actually capable of looking at a quantum system and the quantum information stored in that quantum system and the possibilities of errors occurring without altering the quantum state of the logical qubit that you may encode in a set of physical qubits. And one of the tricks in error correction with superconducting circuits and in error correction schemes overall is to use additional features of the quantum states in which you encode your logical information. And the idea is essentially to try to use the symmetry of quantum states in which you store your logical qubit information by distributing that logical qubit information over many physical qubits. So on the right-hand side here, you see a sketch of what that may look like, where you have, in this case, maybe 49 qubits, 25 of which are used for storing logical information and 24 for error detection. So there's been very clever ideas that have been developed quite some time ago in how to achieve this task of being able to actually look at quantum systems without revealing whether errors occurred, but without revealing the quantum information that is stored in a logical qubit. And so as I said, one of the ways to go there is to use symmetry properties of the quantum states that you use to encode quantum information. And one of those symmetry properties could be the parity. So if you imagine you have a set of 25 qubits, like the red dots that you see here, you could decide to store all quantum information in states of even parity. So states of even parity are those where you have an even number of ones representing the quantum state that you want to encode. And so then one of the ways how to detect whether an error has occurred is to look at whether parity changes, whether your number of ones goes from even to odd. Yeah? And I'll show you a way, according to the surface code and this idea formulated by Kitaev, how you can do that without destroying the quantum information. Good, so in our lab, we've picked the surface code as an encoding for the logical qubit, and it's a two-dimensional architecture, and I think it's an obvious choice for any physical implementation that tends to lay out qubits in a planar lattice. And so superconducting qubits are laid out in a planar lattice. Semiconductor qubits tend to be laid out in that geometry, and also, say, arrays of Rydberg atoms, if they're planar, would be in that geometry. And so what is good about the surface code, it's this two-dimensional architecture. It's all the operations that you need to do are doable in this planar grid of qubits. And the code is topological. So if you detect errors, actually correcting errors locally will actually allow you to deal with the errors that have occurred without requiring sort of global operations on all of the sets of qubits, on all of the qubits in the logical qubit. So what else is interesting about the surface code? So the surface code has a so-called large error threshold, which is about 1%. And this threshold characterizes how good the code is at dealing with errors. And the surface code is one of those codes which has the highest threshold. And so what you're trying to achieve is you're trying to achieve a physical quantum system whose physical errors epsilon are smaller than this error threshold. And when that is the case, and you have a certain code distance d in your error correction scheme, then the logical error epsilon L will actually start to decrease relative to the physical error when you increase the distance of the code. And so this is a difficult task overall, but the surface code is the code that is known best to address this challenge, because it has the highest thresholds, and many other codes have even lower thresholds. And so while we're struggling with getting the errors in our quantum devices down, the surface code is really the way to go here. And for that reason, it has also been analyzed both theoretically and experimentally in most detail. So I should also mention that in our work, we cover quantum error correction with superconducting circuits in this digital approach, where we encode quantum information in qubits. But there's also an alternative approach where you could encode your quantum information in harmonic systems using so-called bosonic codes. And there's been a lot of progress both in superconducting circuits and also in ion traps with using these bosonic code and approaches. considering CAT states or GKP states, for example. And there's been remarkable work both in the ion trap world and in the superconducting circuits world, but I'll be discussing exclusively this qubit encoding in terms of the surface code. Good, so what are the elements of the surface code? So here you see this distance 5 surface code lattice, 5 by 5 physical qubits shown in red, or code qubits in which the logical information is encoded. And these are interspersed with so-called auxiliary qubits, which come in 2 types, the blue and the green ones, that are used to detect both phase and bit flip errors. Okay, and so how does this work? So how do you, and I mentioned already that you would try to detect whether the parity of the state in which you encode your logical qubit information changes throughout your effort to preserve the quantum state of your logical qubit. And this gets done by doing so-called stabilizer measurements. So there are weight 2 and weight 4 stabilizer measurements, and these measurements are measurements of the product of either 4 or 2 Pauli operators. And when you look at this lattice on the left-hand side, you see that 4 qubits surround one of these auxiliary qubits, and the auxiliary qubit is used to measure the parity of the 4 neighboring data qubits. And this parity gets measured both in the Z basis and in the X basis. And so these are, every time when you have an auxiliary qubit surrounded by 4 data qubits, this is a weight 4 stabilizer measurements. And at the edge of such a surface code system here, you see that there's also some weights 2 stabilizers where auxiliary qubits only couple to 2 data qubits in the vicinity. So how is it that you detect the parity of the neighboring data qubit states here? And in this approach, we use auxiliary qubits to do so. You could also think of different ways how to measure this weight 4 parity of the 4 data qubits. So for example, if you had a clever measurement apparatus that could measure that operator directly, you could also think of implementing that. But in this case, we make use of auxiliary qubits to measure the parity. And so here you can see how that works. There's one auxiliary qubit in the Z basis, and you essentially run CNOT gates between the 4 data qubits that surround the auxiliary qubit. And when you look at this and you know how a CNOT gate works, it does nothing to the target qubit when your data qubit is in state 0, and it flips the target qubit when the data qubit is in state 1. So now when you have an even parity state, there is an even number of 1s in the data qubits, and then you swap or you flip the auxiliary qubit state twice. So it goes from one state to the excited state and back. And that's the case for any even parity state. And now if the parity changes from even to odd, say there's an odd number of 1s in the 4 data qubits, this series of gate will actually change the auxiliary qubit state. And that is the way how you can see whether the parity of the surrounding data qubits has changed or not. And so you need to do that not only in the Z basis to detect bit flip errors, but also in the X basis to detect phase errors. And for that purpose, you measure this X-based stabilizers. There's again weight 4 and weight 2 versions. And you can implement that essentially with the same set of gates by changing the basis of your 4 data qubits, moving them from the Z into the X basis and executing the same set of gates. And for successfully detecting the parity of the 4 data qubits in the Z and the X basis, you need to execute these 4 2-qubit gates, and in this case 8 single-qubit gates, and most importantly, you need to do a high-fidelity measurement on the auxiliary qubit state to identify whether the parity has actually changed or not. And for that to be successful, for the surface code, all these operations need to be of extremely high fidelity, so that you actually manage to pass the threshold of the surface code and make the logical qubit better than the physical qubits. And so this is very challenging to achieve overall, and I think people had respect of that challenge, and it took some time to address it appropriately, but there was now very nice progress in the last couple of years on it, and I'll show you our work, the results of our work on that. All right, so maybe I talked about these parity measurements, and just to hammer home the message once more, I show this example here for weight 2 stabilizer with your auxiliary qubit, or which is sometimes called an ancillar qubit also. Yeah, if the data qubits are in state 0, you run these two CNOTs. Nothing will happen to the ancillar qubit. It will stay in the ground state. If the data qubit is in state 1, the first CNOT gate will flip the ancillar, the second CNOT gate will flip it again, and you're back down into the ground state. And so that indicates that if the auxiliary qubit is in the ground state, you see that it's even parity. So now you could imagine that a bit flip error flips one of those data qubits from 0 to 1, and so now you have an odd parity state, you have 1, 0, 1, 1, and so one of the CNOT gates then flips the auxiliary qubit, so the auxiliary qubit changes state and then indicates that your parity has changed. And that you can use as an indicator for an error having occurred, and that works in the Z basis, like shown here, and if you change the basis of your data qubits from Z to X, this also detects the parity in the X basis. Okay, and so in our experiments, physically we don't have CNOT gates available, but we implement CNOT gates as C-phase gates, augmented with surrounding single qubit gates on one of the two qubits. Good, so maybe I'll give you a brief example of how error detection in a very small surface code works, a so-called distance 2 surface code. A distance 2 surface code has a 2 by 2 data qubit grid. It has 3 auxiliary qubits, 1 weight 4 and 2 weight 2 stabilizers get measured here. The stabilizers are listed here with respect to the data qubits that the auxiliary qubits couple to. And you can now ask yourself, okay, what do the quantum states look like in which you store your logical information? And I think it's kind of instructive to look at that. So here is an example for how you could encode the logical 0 in these 4 data qubits. You look at the logical 0 state. It's a superposition between all zeros and all ones. And you clearly see that that's an even parity state. Yeah? And so now you could ask yourself, okay, would you encode an excited logical state? And the way you could do that is you could flip 2 of these data qubit states from 0 to 1 using a logical operator. So a logical operator here is now a string of 2 X operators that you also see visualized here, like an X operator on qubit 1 and an X operator on qubit 4 that would flip 2 qubit states and create this excited logical state. And you look at the excited logical state, and it still has even parity. So now if your error detection mechanism measures the parity, it will not learn whether the logical qubit is in state 0 or 1. But if an error occurs, one of the zeros turns into a 1, the parity will change, and you will notice. So the logical superposition state is a superposition of the logical 0 and a superposition of the logical 1, which is just written down here as the sum of the 2 states above, and you still see its even parity. And you can turn a logical plus state into a logical minus state by changing the phase, and that's this phase operator. And it's an operator where you locally act with a Pauli Z on qubit 1 or qubit 2, or alternatively, qubit 4 and qubit 5. And if you do that, just operating in this way, for example, at the logical plus here, you'll see that you'll turn it into a logical minus. And this state allows you to now measure the parity without learning anything about the quantum information that is stored in this logical qubit state. And that's the basic idea, and that's easy to see for this weight 2, for this distance 2 code, but for the distance 3 code or so, obviously you can look at the properties of these quantum operators here, but if you try to write down the states, it starts to be a bit more messy. So what is special about this distance 2 surface code is it gives you enough information about the errors that occur to detect errors, but you can't correct them. And the first size surface code that allows you to correct errors is the distance 3 surface code. So that is shown here once more. It has 3 by 3 data qubits. The logical operators are strings that cross this code. They have weight 3, so it's 3 operators in a row. The Z operators are horizontal. The X operators are vertical. And in this size surface code, you can correct every single qubit error that occurs, but you can't correct you can't correct all errors of higher weight. So some of the errors that where 2 qubits are affected, you can't detect in this distance 3 code, and then you need to increase the code distance, for example, to 5, and in the distance 5 you would be capable of detecting and correcting 2 simultaneous errors. Okay, so there's 8 auxiliary qubits, in this approach, as I mentioned, we can detect errors without collapsing the logical qubit state that we've created. And in this particular instance, there are 4 Z stabilizers, 4 X stabilizers, 4 of weight 2, and 4 of weight 4. So here's the picture of this device that we've made for this purpose. So the yellow structures are the transmon qubits. Every qubit has its drive line with which we can control the individual qubit state. Every qubit has a flux line that we apply short current pulses to that tune the transition frequency of the qubits, which we use to initiate 2 qubit gates. There's couplers between neighboring qubits that allow us to get the right connectivity for the surface code lattice. And maybe most importantly for us, there's individual qubit readouts with, that enable high fidelity, fast qubit readout with a little crosstalk between the different qubits that are measured. And there's also some level of multiplexing on this device, so there's either 4 or 5 qubits get read out with the same readout line. Okay, and here you see again like how this device now maps into the surface code architecture with 4 weight 4 and 4 weight 2 stabilizers, where the weight 4 ones are in the center and the weight 2 ones are at the boundary. So if you then have this chip and it's designed and made at ETH and in our clean rooms, so you mount it into a sample mount, you package that up to shield it from environmental influences, you get yourself a big cryostats and wire it up and put all your magnetic shielding there. Then you can go ahead and do experiments, and our experiments were all done with a partner on that we're working with since a long time, which is Zürich Instruments, who's a partner in both our EU project and also in a US-funded Logical Qubits project. And so this is the setup in which this distance 3 surface code experiment has been done with the electronics that is in this rack on the left-hand side. And so clearly, the work that we have been doing on this, it doesn't stand on its own. It's based on lots of work that was done in this context by other teams previously. So initially, there were teams that implemented bit and phase flip codes separately, where only one type of error was detected. Then there were first experiments where both types of errors have been detected. And the next step, there were experiments where distance 2 errors in phase and in phase flips and bit flips has been detected repeatedly, but where the code distance was too small to actually correct for these errors. And then now, since about a bit more than a year or so, there's first distance 3 experiments that were successful by our lab, and then also in the ions, and subsequently also by IBM. And there's this nice work by Google that you've maybe seen on the archive, where this distance scaling from 3 to 5 was investigated. Good. So when you have all the bits and pieces there together, then you can first check whether your stabilizer measurements, your parity measurements, actually do work on your device. And for that purpose, you take one of the plaquettes that you see here, like the one in the top right corner. It's a weight 4 stabilizer. And the 4 data qubits that sit at the vertices of that plaquette, you prepare them in all 16 logical basis, in all 16 physical qubit basis states. And you just execute your stabilizer measurement and you see what it shows. And whenever the parity is even, you see a stabilizer value of 1. And when the parity is odd, you see a stabilizer value of -1. And you can check how well that works. And the error is about, for this weight 4 stabilizer, is about 7%, as you see here. And we can model that, and the modeling agrees reasonably well with what we find experimentally. So there's 8 stabilizers on this device. So we measure all these 8 stabilizers, and we find roughly 8% stabilizer measurement error for the weight 4 stabilizers, and about half that for the weight 2 stabilizers. And that's clear why that is, because the weight 2 stabilizers just have a smaller number of consecutive gates that get executed. Good, and so then you take these elements and you put them together in a surface code. So here's the gate sequence for the distance 3 surface code. So in the distance 3 surface code, you have all your 17 qubits, which are listed here. So the scheduling for executing these stabilizer measurements is actually something that was worked out sort of nicely in Leo Di Carlo's group at Delft and is discussed in this paper here, and that's what we've implemented. So in the first part of the error correcting cycle, we execute all the logic, all the 2-qubit and single qubit gates for the Z stabilizer measurements. In the second part of the cycle, we execute all the gates for the X stabilizer measurements. And one aspect that is now special in our arrangement here is that while we execute one type of coherent gates for the stabilizer, we measure the auxiliary qubit states of the other stabilizer simultaneously. And this is possible because our auxiliary qubit measurement has low crosstalk with any of the other components of the device, and it's also high fidelity, and the cycle time is short at about only a microsecond. Okay, and so then you go ahead and execute this gate sequence here. You prepare the logical 0, the logical 1, and the logical superposition states that I had introduced. And then once you've done that, and that works deterministically, you run this cycle n times for preserving the logical state. And yeah, as I said, the cycle duration is short. And maybe one particular aspect that I should mention is that leakage is detrimental for quantum error correction, and leakage gets detected. Leakage out of the computational subspace of the physical qubit gets detected in our experiment and then dealt with. Good, and what is also maybe interesting to know is we execute this cycle for a maximum of about 16 times, and when we do that, we execute about 800 single qubit gates and 400 2-qubit gates. So it's a fairly deep circuit at that level. Good, so how do we analyze how this works all together? Here you see our distance 3 surface code. In the end, we go ahead and measure the logical Z and the logical X operators, which are these strings of 3Z or 3X operators along verticals or horizontals in this code, as you see on the right-hand side here. We prepare the logical 0, 1, and plus and minus states. We perform the error correction cycle. At the end of the error correction cycle, we read out all the data qubits to check what their state is. And we determine the logical operator expectation value by just multiplying the individual logical operator measurement outcomes. And what is important, we take into account the outcomes of all the measurements of the auxiliary qubits that happened in the n cycles of the error correction. We decode that information with a minimum weight perfect matching algorithm, and we correct the final outcome to take into account for the errors that may have occurred, and apply that correction to the final measurement result and see whether it improved the logical performance. And in the end, you just average over many repetitions of that experiment, where for every individual repetition you have detected and corrected for the errors. Good, so here you see how that experiment, what that resulted to. So this is the logical operator expectation values, how they change with the number of error correction cycles. You see that the error accumulates, so the logical qubit still decays. It's not perfect yet. The logical lifetime is about 16 microseconds here, which is much larger than the error correction cycle time. The logical coherence time is about the same. And we can understand this performance so reasonably well by comparing it to sort of full numerical simulations of this system. And there's a little bit of a gap between what we would think the performance would be because of the constraints that we considered in the numerical simulation. And I could explain that more if you're interested. So from this decay of the logical qubit state, you can now evaluate the performance of your logical qubit. Essentially relating this logical lifetimes to the cycle times. And you can evaluate the logical error and how the logical error increases with the number of error correction cycles. And from that increase, you can determine the logical error per cycle, which is a good quantity to characterize your error correction scheme. And the logical error per cycle is about 3%. And so maybe one of the interesting bits to appreciate here is, so you have these stabilizer measurements, yeah? The error in the stabilizer measurements, if it's weight 2, is 4%. If it's weight 4, it's 8%. You put 4 stabilizers of weight 4 and 4 stabilizers of weight 2 together in an error correction cycle. And nevertheless, by looking at the outcomes of these error detections, you can create like a system performance where the logical error per cycle is 3%. Yeah, I think that in itself is kind of interesting to notice, yeah, and really shows that this quantum error correction idea overall works. And obviously that was understood on the theoretical level, but it's good to see that work also on the experimental level. Okay, so how do we do in comparison to the other experiments? So there was quite a bit of progress. So there's this Honeywell experiment that was published sometime summer last year after this nice work from Chris Monroe's group that executed their error correction cycle only once, but it was also a nice Nature paper. So and after that, then there were a number of works which implemented distance 3 error correction in the surface code. Yeah, in our lab, and then in John Y. Pan's group at IBM, and now the nice experiment by Google also. And so you can look at how well did these experiments do, and one of the quality criteria is this logical error per cycle, which is plotted here. And the experiments, they essentially come out all around a few % logical error per cycle in this distance 3. Yeah, this one here was a little bit worse. The superconducting circuit experiments, they all come out with cycle times of maybe around a microsecond or a bit slower than that, but certainly a few microsecond cycle times. And if you compare it to ion traps, for example, where repeating the error correction code requires doing measurements on the auxiliary qubits in every cycle, and in the ion traps that requires shuffling ions around, and shuffling ions around is slow, so the current kind of wall clock cycle time in ion traps is 5 orders of magnitude slower than in superconducting circuits. And obviously what that then means exactly, like once you would build a larger quantum computer, that really depends on lots of other aspects that one has to analyze later. I think you shouldn't interpret this as oh, it's never going to work with the ions. I think the path for a full-scale error-corrected quantum computer is still long enough or so that maybe this is only indicative of where things will go. Good, so these are two relevant metrics, I think. And I think sort of another typical metric that gets discussed is how well does your logical qubit do in comparison to the physical qubit coherence? And that's an important metric, but it's really not the only thing that matters. And for example, Chris Monroe will not get tired to tell you that their ion qubits essentially have no decoherence, and therefore it's not a problem at all. But there is control errors, and in the end, you have to make sure that that you're able to combat both decoherence and control errors and do good gates between your logical qubits. So one of the things that we looked at together with Marcus Miller was to look at what would be needed to do a 2-qubit gate, a logical 2-qubit gate. And a logical 2-qubit gate, sort of maybe the simplest way to implement that is to do a transverse 2-qubit gate. So in a transverse 2-qubit gate, you could essentially have 2 distance 3 logical qubits. And you can enact your logical 2-qubit gate by doing pairwise C-naughts between all the data qubits. And in that case, what you would compare your logical error per cycle against is the physical 2-qubit gate error, which in our experiment is about 1.5% or so. And so one of the questions that you could ask yourself, one metric that could be interesting is to ask, okay, when is the error for doing a logical 2-qubit gate similar to the logical state preservation error in a single cycle? And that is what is plotted here. The 2-qubit gate error versus the logical error per cycle. And to see how well we do is we've done numerical simulations where we've sort of fictitiously thought what would happen if we were to improve the performance criteria in our device by a factor of 2, 5, or 10. And then we look at where kind of our 2-qubit gate performance crosses the logical error per cycle. And so this indicated to us that maybe in our current performance we're not better than the break-even point in our device, but we're likely maybe a factor of 2 away from that. And so I think that sounds encouraging. It would encourage us to do a next-generation device here. And we've also done Pauli error model simulations that essentially come out with a similar result. So with that, maybe let me wrap up. So we've implemented repeated quantum error correction in a distance 3 surface code at a short cycle time of about a microsecond. The logical error was about 3% per cycle. I think it's close to break even, and not below it. And certainly there's next steps that we would be interested in realizing. Maybe a good one is clearly doing gates between logical qubits, but also using feedback and reset operations, and also investigating a bit more how our logical qubit performs when we inject noise into the system. So with that, I should thank our whole team, both the experimenters and the theorists again. So I would invite you to talk to Graham and Ans, who are here, and also Christian, who is here. And I'd like to thank you for your attention, and also thank our whole crew at ETH for their continued effort on this. So this was essentially last summer. I think where Switzerland allowed us to meet again, and I think the threshold for meeting outside without masks and anything was 50, and so there's 49 here. So we were, and you see everyone was happy, and we weren't scared of being with beer bottles on this picture, I think. So thank you very much, and in case that anybody is looking for something interesting in an academic lab to do, we're always looking for good additions to our team. Thank you very much.
Well, thank you very much, Andreas. We'd like to open it up to questions now from the audience. We have a few hands.
Yes, I wanted to ask about what do you think that are the errors that are present in the device but not captured by the simulation, like both for the lifetimes and the stabilizer parities?
So maybe I wonder whether we did the good choice for what to display. I think we have included more parameters in our device modeling, and you can make it fit always. Yeah. So I think if we were conservative, we didn't want to overinterpret our ability to really exactly model what is going on in the device. One of the aspects that is not taken into account in the data that is in the simulation data that is presented here is the fact that the coherence of the qubit changes while we operate the 2-qubit gate, mostly because we do a C-phase gate and the qubits are idled at their flux noise insensitive points, but they do gates where they're sensitive to flux noise. And that's an aspect that you can model, and we've done that, and then the agreement is better, but we chose not to when presenting this data. And maybe it was a mistake because everyone asks this question. Yeah? But I think what we were worried about is that there's enough degrees of freedom in your numerical simulation that you can sort of always make it fit, yeah? And whether you really interpret it well or not is a different question, and you couldn't tell from just looking at this curve, so we decided to keep it like that.
Okay, other questions?
Hey, thank you for the talk. So from the picture of the device, I was just wondering, it looks like each second qubit, the readout line is like more coupled to the qubits than the other.
Yeah. So this is also a question that we sort of always get, which is good, and so it's also a question that you only get when you allow people to look at your device. Yeah. When you don't, you won't get that question, and so it's a good observation, and the reason is that sort of these ones here. The qubits that you see here, they come in two flavors. We have data qubits and auxiliary qubits, and the data qubits have a larger detuning from our readout resonators. And to still get good readout performance for this device, we decided to couple them more strongly to our readout resonator, so that at a given detuning, you would get a similar chi shift, and that's the reason for it. So they come in these two classes.
Okay, thank you.
Question over here.
Yeah, there's a few in the back also.
Yeah, sure.
So there's one place where you have to put the readout resonator between the qubits. Is that going to be a problem when you increase the number of qubits?
So yeah, this is this side here. So
Yes.
so interestingly, in 17 qubits, it doesn't look like it when you look at it for the first, but everything is on the edge but one qubit, and so there's only one qubit in the center, which is this one here, where we chose to place the readout resonators sort of within this 4-qubit plaquette here. Yeah, and it's not nice. It leads to problems, and certainly at some stage when you want to scale this, you probably need some 3D integrated version of that. And I think in that end, the work at Google and IBM is probably a bit more advanced than ours. But I think we can sort of push this a bit more. And in principle, you want a copyable unit cell that you can repeat on this device, and here we just did go for this solution, which we thought was practical, and it has a few issues that you need to address, but which we addressed well enough on the for this particular device. And I can tell you a bit more about the details, but they're not that interesting, and so I'll
do you actually see like reduced coherence times around that readout resonator, or maybe increased crosstalk?
Yeah, there's some in, like, for example, the routing of this drive line to that qubit increases some of the crosstalk, but I do think if you have proper 3D integration, I think you can probably deal with these things. And so we have some active crosstalk mitigation by kind of interferometric cancellation by applying just the right tones on gates which couple to each other.
Thank you.
That's also a good observation.
Thank you.
No worries. Some in the back.
Thank you very much. To what extent is leakage to higher excited states impacting the results here, and how do you see it for the upcoming generations of going to larger chips? Is it a big concern?
Good, yeah. So I've not talked a lot about leakage. It's an important question. I think our so we have there's two types of leakage in our device. So our data qubits have quite small leakage because they don't cycle through their second excited states. The auxiliary qubits have leakage, so we're currently rejected. It's and this is discussed in the supplementary material of our work. We've also where we have the data also analyzed without rejecting that leakage. And obviously, in next generations, you would want to actively mitigate leakage by either through resets or using gate-based methods to deal with leakage. And there's ideas how to do that, and some of that has been implemented or thought of, in for example, in the ion trap context, where interestingly leakage is also a problem. So it's a very it's a very important aspect to consider here, and I've not discussed it here, but it would take, say, extra 5 minutes or 10 to give it full justice. I've also not said anything about the decoder, for example.
Okay, we have time for one more question.
Yeah, you're ignoring the people in the right and the right backhand side, so maybe you should pick you.
Thanks for the great talk. Maybe related to the questions that were asked previously. So in the Google work on the exponential suppression of bit or phase flip, they needed to do dynamical decoupling during the readout, and they have flip chip. So I'm wondering, like, how is it that here there was no need to do this dynamical decoupling?
We also do dynamical decoupling. I didn't show you the actual gate sequence that we implemented. I showed you the CNOT-based gate sequence, but indeed our stabilizer measurement has dynamical decoupling pulses in the middle of the cycle of each stabilizer. I do think if you read the supplementary material of the Google paper very carefully, I think there's the need for doing this dynamical decoupling very seriously for them, is they have a much larger device, and the way they implement the gates comes with maybe some downsides. So for example, if I understand it correctly, they don't idle their qubits at their flux insensitive points, but they idle them at other frequencies because of two-level defects, and that then requires, to keep the performance high, it requires more work on dynamical decoupling, but there's some dynamical decoupling here as well.
So I'm afraid we'll have to move on. So if you have follow-up questions, please, meet Andreas during lunch or during one of the breaks. But in the meantime, let's thank Andreas again for his talk.
Thank you.
And so with that, I would like to welcome Amy Greene to the stage. And Amy will talk about, from MIT, will talk about coherent error mitigation and density matrix exponentiation. using emulated quantum measurements. Thank you.
Good morning. It's a pleasure and a privilege to be here speaking with all of you face to face. And I'm really glad that I have this opportunity to share with you the work that I've been doing on this new error mitigation technique called quantum measurement emulation, and how we're using it to mitigate coherent errors and how it enabled us to run an algorithm called density matrix exponentiation. I do experimental work with superconducting qubits in Will's group, and here's the obligatory dilution refrigerator picture, and here's an SEM image of the device used for the work in this talk. It's of a slightly older generation, so we have 3 directly coupled transmon qubits, and all 3 qubits are flux tunable, so note the local flux and microwave drive lines. Directly before this work, we ironed out our procedure for calibrating high-fidelity CZ gates, and we wanted to use those gates to implement a nifty algorithm called density matrix exponentiation, which has applications in quantum machine learning and beyond. But while we were working on this implementation, we struggled with coherent errors, which were deleterious for our performance. And in order to handle those coherent errors, we developed a new error mitigation technique called quantum measurement emulation. So in the first part of this talk, I'm going to be describing quantum measurement emulation, or QME. And in the second part, I'm going to describe the implementation of the algorithm density matrix exponentiation, or DME, which was enabled by QME. And yes, the similarity of those 2 acronyms has been very confusing. Hindsight is 2020. So I'm going to begin this talk by reviewing common error channels in quantum computing. And I'm going to lump them roughly into 2 groups. Incoherent errors are stochastic, and a very common example of an incoherent error is the depolarizing channel, where the state sinks uniformly into the center of the block sphere. Dephasing errors are also a common incoherent error channel, which is associated with measurement, where the state is projected onto an axis of the block sphere. In contrast, coherent errors are deterministic rotation errors which preserve information. Of these 2 types of errors, this talk focuses on dealing with coherent errors, which I'm going to try to convince you are the more pernicious. And to convince you of that, I'm going to try to give you some intuition for how these different kinds of errors scale. For incoherent errors, I'm going to use a depolarizing channel as an example. With some probability p, the qubit's density matrix is replaced with a completely mixed state, here written out as I rho I plus x rho x, etc. And with probability 1 minus p, the density matrix stays the same. After the error channel has been applied twice, the probability that no error has occurred is 1 minus p squared. And after the channel has been applied n times, the probability that an error has occurred is 1 minus p to the n, which looks like np for small p. So we're seeing that for incoherent errors, the probability of an error occurring scales linearly with the error strength and with the number of applications. Now let's turn to coherent errors. I'm going to use a small x over rotation as an example that brings us from the intended 0 state to the 1 state. And after the error has been applied n times, the probability of measuring the erroneous 1 state goes like sine squared of n epsilon, or like n epsilon squared for small epsilon. So what we're seeing here is that incoherent errors scale linearly with the number and strength of the error, but coherent errors can scale quadratically. And I want to show you how this plays out in the data that we take. Benchmarking techniques such as Clifford randomized benchmarking and also cross-entropy benchmarking are designed to model errors as a depolarizing channel in order to get one convenient number out. And to achieve this, random gates twirl the errors to make them all look like a depolarizing channel. And we see a smooth monotonic decay. So here, for instance, is the randomized benchmarking curve for our 99.7 CZ gate. But this process can mask coherent errors. So when we take a same CZ gate and repeat it in a chain, we can see a very different performance, these big oscillations in fidelity that correspond to coherent errors accumulating and then wrapping around the block sphere. The difference in performance is substantial. By the 12th cycle of the circuits, the fidelity for the CZ chain has dropped precipitously, while it is substantially higher for the randomized benchmarking chain. So here we're seeing the unfortunate scaling of coherent errors playing out in a way that impacts the results of our experiments. But we can take a cue from randomized benchmarking as to how to address these coherent errors. We can very thoughtfully add random stochastic gates to make our coherent errors look incoherent. And when I say this, I imagine that randomized compiling pops into your mind. It's a fantastic example of employing this strategy, which was developed by Joe Wallman and Joe Emerson. And in randomized compiling, if you have some error-prone gate, twirling gates are inserted before and typically drawn from the single qubit polys, and after the error-prone gate, chosen to keep the intended unitary the same. So for example, let's say we're trying to do an identity operation. There's a little bit of extra X rotation going on. The original gate will be replaced stochastically with one of these 4 circuits. Here are the unitaries associated with each. And when the experiment is run, we randomly draw from these sequences an average over the ensemble. When we average over the matrices, this is the operation that's produced. It's non-unitary, and it uniformly shrinks vectors. Randomized compiling has turned this coherent error into a depolarizing channel. So the error mitigation technique that I want to introduce to you in this talk, quantum measurement emulation, similarly makes coherent errors look incoherent. But there are a few key differences. And one of the main ones is that QME was designed to be used with stabilizer codes. And another key difference is that instead of turning coherent errors into a depolarizing channel, it turns them into a dephasing channel. Namely, quantum measurement emulation emulates the measurement of the stabilizers of stabilizer code, and coherent errors that are transverse to the axis of that measurement are turned into a dephasing channel. One of the nice features of this is that QME can be tailored to the device that you're working with. I invite you to consider the 3-trans-1 device in this talk as a toy example. And for the CZ gates on this device, they are prone to having a ZI type coherent error, which arises from low frequency drift in the flux. And when we think about trying to create logical qubits on a device such as this one, we create a code that protects specifically against this very biased kind of coherent error that the device experiences. And QME randomizes along the axis that specifically addresses the biased noise rather than randomizing uniformly across all axes of the Bloch sphere like a depolarizing channel. So this is an advantage of a dephasing channel over a depolarizing channel when the coherent noise is biased. Now, I want to take a step back and describe what I mean when I say quantum measurement emulation and how it acts as a dephasing channel. And let's start by considering very quickly what happens during measurement of the z-axis, measurement without feedback. I'm showing you a diagram on the left and tomography data on the right. Some probability, we measure a 0, some probability a 1, and the net effect on the ensemble is to project the qubit state onto the z-axis. I'm going to show you this again, varying the initial state. But we can create the same quantum channel much more quickly using probabilistically applied single qubit gates. With probability 1/2, we'll apply an identity gate, which leaves the state where it is. Probability 1/2, applying a z gate, which rotates the state around the Bloch sphere. And when we average over the ensemble, this projects the state onto the z-axis. And again, varying the initial state. With probability 1/2, apply an identity gate. Probability 1/2, apply a z-gate. And the effect on the ensemble average is projection onto the z-axis. Here, side by side, we can see that z-axis measurement and this probabilistic z-QME creates the same channel. It emulates z measurement. In fact, with the correctly chosen gates, we can emulate measurement along any axis. Here, by probabilistically applying an X gate, QME emulates X-axis measurement. And emulating the measurement of a stabilizer is as straightforward as emulating a single qubit measurement. To measure, say, a ZZ stabilizer with probability 1/2, we apply an identity, now to both qubits, and probability 1/2 a Z-gate, now to both qubits. I'd like to show you how this plays out on an actual circuit. And using a very simple circuit, this is just a chain of CZ gates, since that's the dominant source of coherent error in our systems. And to add error mitigation, I'm inserting QME between every pair of CZ gates. Here in some data taken on the device I shown you in the previous slide, we can see how QME leads to improvement. The uncorrected trace in gray has the dip and revival, which is characteristic of coherent errors, while the green trace, where QME is applied, has the smooth monotonic decay, indicating that the coherent errors have been rendered incoherent. And we're also seeing overall higher fidelity from the trace with QME. In simulation, I compare the performance of QME to randomized compiling. So to perform randomized compiling, I'm adding twirling gates in the same places as the QME operation. And here you can see that adding QME gives similar performance benefits to adding randomized compiling, even though randomized compiling has a few extra compilation steps involved. To sum, one strategy for mitigating coherent errors is to make coherent errors look incoherent by stochastically adding gates. And quantum measurement emulation is a technique that does that by turning coherent errors into a dephasing channel. It can be used for state stabilization, think quantum Zeno effect, but I think it's most exciting to be used for error mitigation with logical qubits. That said, it's QME's application for state stabilization that enabled us to run a demonstration of density matrix exponentiation, which leads us to the second part of this talk. Density matrix exponentiation is a very efficient technique for transferring information from one potentially multi-qubit instruction state to another target state. It can be thought of as generating quantum instructions and scales logarithmically with the dimension of the instruction state, which represents an exponential reduction in resources compared to tomographic techniques. It's a building block for several different applications of interest, including quantum principal component analysis, efficient measurement of entanglement spectra, sample Hamiltonian simulation, quantum semi-definite programming, and also universal quantum emulation. And I'm not going to dig into all of these right now, but I'm trying to convey here that density matrix exponentiation is an interesting operation to look into. So what exactly is density matrix exponentiation? It's exactly what it sounds like, taking some instruction state of interest represented by the density matrix rho and exponentiating it, performing the operation e to the minus I rho theta. Now, this is actually not a linear operation, so it can't be implemented simply by applying the right unitaries. But a few years back, Seth Lloyd and Iman Marvian figured out an algorithm that approximates density matrix exponentiation by trotterizing the rotation and taking a new copy of the instruction state during each trotterized step. And as you might expect, the precision of this approximation improves as the number of steps increases. Each step involves a delta swap gate, where here delta swap is just the notation that I'm using for a partial swap operation. So in the algorithm as initially conceived for each trotter step, a new copy of the instruction state is brought in, a delta swap is performed with the target state, and then the instruction state needs to be reset and reinitialized. And the key insight that allowed us to do an implementation of density matrix exponentiation was to use quantum measurement emulation in order to approximately reset the instruction state after each step. And as you might expect, using QME to approximately reset the instruction state does add some additional error. But this additional error is of the same order as the approximation error. And all of us in this room know that the constant coefficient is important, so I'm going to share a spoiler with you from later slides in this talk and say that for the demonstration in this talk, the error added from QME is about 1/5 of the error added for the approximation. And using QME in this manner enables us to perform a demonstration of density matrix exponentiation using just 2 qubits on this 3-qubit chip. One is the target qubit, and one is the instruction qubit. When I first learned about density matrix exponentiation, I found it a little bit confusing, to be honest with you. So I want to walk through a quick example. So here we're using the instruction qubit in the plus state, and the density matrix looks like so. And when we plug in and do the math for the exponentiation, we find that we get out an X rotation. So we're seeing a rotation about the axis defined by the instruction qubit. Now, you might be sitting there thinking to yourself, well, this seems like an awfully convoluted way to implement an X rotation. But the key thing to notice here is that here the axis of rotation is not being set by some classically predetermined sequence of pulses, but rather by information stored in the quantum state. And here I'm going to indulge myself with a comparison to classical computing. And classically, it was the ability to dynamically generate instructions which moved us from adding machines to truly doing computation. Now I'm going to walk through this example visually, and here I'm leaving out the QME for the sake of simplicity. So we're starting out with the instruction qubit in the plus state and the target qubit in the plus I state. Do a small delta swap, get a new copy of the instruction qubit, do another small delta swap, reset and refresh the instruction qubit, another delta swap, and so on. And all of these small delta swaps, when combined together, build up the total desired rotation. Now that I've talked through the physics of this, I want to show you some tomography data. The outcome of density matrix exponentiation is a function of the instruction state, of the total angle subtended, and also of the number of steps taken. So when I tell you that I'm going to show you tomography data for a plus x for pi half DME operation, it's going to look like doing an x rotation, pi half x rotation in 4 steps. And again, we're starting with the instruction state in the plus state and with the target state in plus I. And I'm showing you tomography data as we slowly build up the circuit for each of 4 steps, ending up with the desired rotation. In order to properly characterize the performance of DME, we use process tomography to measure the operation produced by running DME with a particular input state. And then we calculate the process fidelity between the measured and expected operations. And to get a sense for how DME performs, we did this varying the initial state of the instruction qubit. I'm about to show you a few different values for the process fidelity, changing how much we included in the simulation to get the expected operator. First, I'm showing you the fidelity to the ideal nonlinear operation, e to the I rho theta. Recall that this idealized density matrix exponentiation is nonlinear and can't actually be realized with a unitary acting on both qubits. There's a small number above each of these columns, and this corresponds to the number of steps taken in running density matrix exponentiation for each instruction state. And for each instruction state, we varied n and picked the one that led to optimal performance. And there's a trade-off here between increasing the number of steps, which lowers the algorithmic error, but also increasing the number of steps makes the circuit longer, which leads to the accumulation of gate errors, which here are largely incoherent errors. This next value that I'm showing you is the process fidelity when we compare to the operation produced by the DME algorithm, where we take new copies of the instruction state for each characterized step. And finally, I'm showing you the process fidelity compared to running the algorithm using QME to refresh the state. And when we look at the difference between these 3 different numbers, we can see how much error arises from the approximation, how much from adding QME, and how much from the error in the gates themselves. And for this last, we're seeing 91% process fidelities when we average over all of the instruction states. So in sum, I've shown you a demonstration of density matrix exponentiation on a small superconducting qubit processor enabled by this new error mitigation technique called quantum measurement emulation. And we've demonstrated process fidelities close to 90% for circuits at a depth of 73 gates and explored the trade-offs between the algorithmic error and gate coherence errors. Now, density matrix exponentiation, as initially conceived, was intended for a quantum machine learning algorithm, namely quantum principal component analysis. But it represents a new paradigm for performing computation using quantum instructions. And earlier I flashed a slide where we showed many different applications that are taking advantage of this new paradigm, but we think that we've just begun to scratch the surface of what we as a research community can do using quantum instructions. And we hope that this demonstration of density matrix exponentiation will spark interest in further exploring more applications. And with that, I'd like to thank my team, and thank you, and I'd be happy to take any questions you have in any time that remains.
Thanks, Amy. I'd like to open it up for questions. We have one here.
Yeah, thanks for a nice talk. At some point when you talked about the QME, at the last slide, suddenly there also popped up like a dynamical decoupling thing that showed to turn out not to do anything, and I was a bit surprised that it actually didn't improve anything. If the error is like a set error, I would have imagined that an echo-type dynamical decoupling would have improved. So can you say a few words why the dynamical decoupling did not?
Absolutely, it's a great question. So coherent errors are associated with gates, and dynamical decoupling is an error mitigation technique that's designed for errors that have a time symmetry associated with them. So dynamical decoupling, you echo out the errors by sort of folding them back on themselves, and there's this time symmetry that's required to do that. And so for dynamical decoupling to be advantageous in a circuit, that circuit needs to have the right symmetry for dynamical decoupling to echo out the errors. And in the circuit that popped up in that plot, which is different from the CZ gate circuit, actually, that was on me, that circuit didn't have the right symmetries for dynamical decoupling to echo out the errors as shown without a more serious calculation to figure out where it should be inserted. Does that answer your question?
Yeah, great, thank you.
Any other quick questions before we move on?
Hi, Amy. Excellent talk. So can I just go back to one of this plot where you showed the fidelity oscillates as a function of number of gates? Are those so what are those fidelities? Are those from randomized benchmarking or some other?
Oh, that's the state fidelity.
Sorry?
That's a state fidelity number that you're seeing.
Okay, thank you very much.
Okay, with that, we'll have to move on. Let's thank Amy again. Okay, and with that, let me introduce our next speaker, Eli Levenson-Falk from the University of Southern California. And he will be speaking today on engineering and harnessing noisy environments to preserve quantum process fidelity in superconducting qubits.
So thank you. Thanks, everybody, for coming. This is really fantastic. I, of course, need to start out by acknowledging the people who actually did all this work. So my students, Evangelos, Darian, Sasha, and Haimong, who collected all the various data, and then our theory collaborators, Jeffrey, Tamim, Lee, and Justin. And the idea here in this work is actually much more maybe basic physics focused than application focused. We're trying to emulate open quantum systems. So we know how to do this with closed systems. A theorist can give me some Hamiltonian and say, hey, what does this actually do? I can't solve it analytically. And okay, I can translate this into gates using a known recipe. I go to my large-scale fault-tolerant quantum computer, and I plug it in, and I simulate, and I get an answer, and I get tenure, and everyone's happy. Now, most of the work right now is that we're going to be talking about is making that large-scale fault-tolerant quantum computer. But I want to ask a slightly different question here. What if the system is open? Well, we have theoretical descriptions of this. We've got master equation descriptions. Got a pointer here? No. I do. So here we've got basically coherent evolution. This is the closed system dynamics of our density matrix. This is an open system effect of just a Markovian decoherence, described by this Lindblad operator here. So this is an environment that has no memory decohering our circuit. And then over here, we've got an environmental decoherence that may have some memory kernel over past evolution. And so this is a non-Markovian effect. And so they hand me this and they say, hey, what does this do? And not only do I not know, so I not have my large-scale hardware required to do this, I don't know what that hardware is. We don't really know how we're supposed to do this. We have some ideas of probably what we need. We probably need environments where we can tune the coupling fast, and by fast I mean on the timescales of these interactions. We'd like to be able to tune this coupling among multiple axes. So for instance, if this is a qubit as my system, I'd like it to be able to couple to the environment along sigma x, sigma y, sigma z, maybe non-Hermitian axes, maybe like just a sigma minus. We want to be able to tune the environment itself in the sense of like giving it some finite amount of coherence or dissipation, tuning the exact nature of its memory, and really want to be able to just throw as many tuning knobs at this problem as possible. So we're going to need new hardware. So the first set of experiments that we're working on here, and I apologize, this is not rendered correctly. Sorry. Okay. Sorry, that's not going to show up right. We have a specific master equation where we have a Markovian environment here, so just general decoherence, and then a particular type of non-Markovian environment. This is known as a generalized Markovian master equation. It's described in this theory paper by our collaborator, Jeff Marshall. And the idea here is that there's a memory over past evolution described by this kernel function K. And what this does is it takes you from this sort of standard exponential decay of coherence to an oscillatory decay of coherence with a longer timescale. So there's actually a preservation of coherence here due to adding a non-Markovian environment. And the question really is, could we recreate this using noisy classical control signals? So the simplest thing possible, we're just going to take our standard qubit control techniques and try to make a quantum environment out of them. The technique here is to replicate this quantum environment with a noisy control tone, B of t, that has a classical autocorrelation, function of this classical control tone, which is equal to the quantum memory kernel. So the theory paper says this will work. We need to test it, and we're going to test it by, and again, this didn't render correctly, looking at the qualitative behavior and the quantitative extension of coherence. So we need to pick a memory kernel. The first one we'll pick is a memory kernel which just decays exponentially in time. So the system has some memory, but the further back you go, the more that memory goes away. Well, a classical signal that reproduces this autocorrelation is just telegraph noise. Telegraph noise with a switching time of tau k, which is this memory time. So that's very easy to implement. What we do is we take a qubit, we're going to drive it noisily along one axis with just white noise. So this is to reproduce a Markovian environment. The qubit's background environment was probably reasonably Markovian, but we wanted to make sure it was 100% Markovian to really get to the full limit here. So we're just driving it with white noise. And then on a perpendicular axis, we'll prepare our initial state. Here it was the excited state. And then drive with our telegraph noise. Repeat this many, many times. Generate a new instance of these noisy drives every time. Sweep the length and measure. And what you see is a really great agreement with the prediction from theory. So it's actually a little hard to tell that these are separate curves. On the left here in black, we've got the analytic solution of the master equation that was worked out by Jeff in his paper. In red, hiding behind there, we have stochastic Schrodinger equation trajectory simulations. And in blue, we have our data. And they lie all right on top of each other. We get this nice oscillatory behavior we get an extension of the coherence to twice the initial coherence time. On the right, I'm showing just the envelope of this decay, so just basically this exponential piece right here, as a function of this autocorrelation time, tau k, basically as a function of the switching time of this telegraph noise. And you can't quite see because they lie right on top of each other, but there are dashed lines behind all those markers, which indicate just the theoretical predictions. That's not a fit, that's just a zero parameter prediction. So it works really, really well. We can emulate the master equation really well. And hey, we got some coherence for free, which sounds really great until you look at the sort of best case scenario here, which is when the autocorrelation, tau k, goes to infinity. And in that case, it's a Rabi drive. We're just driving the qubit constantly and never changing anything. So that's maybe a little bit on the boring side. Maybe we can do something more complicated. So let's take a more complicated kernel, a more complicated memory. Now we still have this exponential decay of memory, but there's an oscillatory component added to it. The environment's memory is actually oscillating. And it's oscillating with this frequency nu. And what we find is that we can do this sometimes. When the strength of our drive, the strength of our noisy drive, is small, particularly the Rabi frequency that you would get from it is smaller than nu, we get really excellent emulation of the master equation. These two curves lie right on top of each other. But as we increase the strength B naught here, we start to lose some of the quantitative and then really the qualitative features. What's going on here is basically a breakdown of some of the approximations that led to being able to emulate this environment with a classical tone. However, I do want to note that the actual envelope of these curves, the exponential decay part, always stays the same. So we're able to emulate that part. All right, so it works sometimes. Classical control can get you some of the way there, but it doesn't work all the time. And maybe that's obvious. It's classical. We're trying to do something quantum here. So really we want an engineered, noisy quantum environment. And okay, the first thing you're going to need for that is dissipation. Specifically, you want customized dissipation, and ideally dissipation that can be modulated. So at a master equation, that's going to be a Lindblad. Experimentally, that could look like many things. Our idea here is to have a parametric coupler to do active dissipation. So let me walk you through this device. The idea here is we're going to have a target system. In this case, it's a linear cavity, a linear resonator. And we'll couple it to this device we call a dissipator. It's really just a parametric coupler, looks like a tunable transmon, coupled to some lossy feed line. So we deliberately make this thing very, very lossy by just coupling it to an external feed line and putting a nice termination on that. And we can drive a flux through this squid here to parametrically pump this device. Now, this dissipator and the cavity are far detuned from each other. But if we pump the dissipator at the detuning frequency, we will induce a resonant swapping interaction that swaps excitations back and forth between the cavity and the resonator. Cavity and the dissipator. And importantly, because the dissipator is lossy, when an excitation goes into the dissipator, it immediately decays away. So if we just drive constantly, we'll take a cavity that has n photons in it and bring it all the way down to the ground state. Now, again, we're going at the master equation emulation, but this is actually a very practical device. Many of us have qubit coherence times that are limited by the fact that our cavities have thermal photons in them. If I put a regular transmon qubit, or just any good logical qubit in this cavity, the photons in that cavity will measure the qubit when I don't want it to be measured. They'll dephase it. And so by making sure that these photons are very quickly removed before they have a chance to interact with the qubit, I'll actually preserve the coherence. So we've simulated this. Here is a simulation of a cavity that starts with one photon in it, with and without the dissipator being driven. Without the dissipator, the cavity will just decay with its ordinary cavity decay rate kappa, and it'll end up at some asymptotic value here, which is given by a temperature. Basically, we're simulating a cavity at a finite temperature. I believe in this case it was 50 millikelvin. When we turn on this parametric drive, we very, very quickly eliminate any photons that are in the cavity, but we also bring it to a much lower level. Now, I want to emphasize here, the dissipator circuit in this simulation was also at 50 millikelvin. The interaction we bring, that we drive with this parametric pump does not bring these into thermal equilibrium. It brings them into excitation number equilibrium. So in this simulation, we put the dissipator at a higher frequency than the cavity. So at the same temperature, it has far fewer excitations. This is a refrigeration process. You can write this down as a thermodynamic refrigerator, and in fact, I believe it satisfies the Carnot limit. Now, we've made this device, or more accurately, Lincoln Lab has made this device from our design, so thanks, Will. The Foundry program has been excellent. And just have some initial results on it. We can see an avoided crossing with the cavity when we tune through. We very clearly see the cavity resonance disappear, indicating there's a lot of loss. Unfortunately, we did this a little bit too well, and this device is so lossy that it's actually really hard to drive. So we're going to back up a little bit with the next version, and I hope to show you results on that soon. All right, the last thing I want to talk about is trying to do something maybe even a little bit more sophisticated than this. Again, this is just going to be loss. It's loss that I can modulate, so maybe I can get some non-Markovianity there. But I'd really like something more general. And perhaps the most general thing I can do is take a density matrix and do a completely arbitrary feedback based on it. So we're going to do this using weak measurement. The idea here is that we continuously drive a very weak measurement tone onto a qubit, onto a measurement cavity, extract information continuously. If we amplify that with good quantum efficiency, we can reconstruct the density matrix in real time. And what I've drawn here is sort of the ideal setup that I want. So I've got my qubit in a cavity. Here, I'll use this. I've got my qubit in a cavity. I'm measuring it with some measurement tone. That comes through. I amplify this measurement along some axis. And then I'm going to reconstruct the density matrix from my measurement voltage and perform completely arbitrary feedback functions here. I've drawn this as sort of a PID loop. I can depend on the measurement, on the derivative of the measurement, on the past integral over the measurement, but really anything I want. Now, this is going to be hard. This requires really fast processing. Luckily, modern electronics can do this, and we actually have a collaboration going with quantum machines, who you can talk to at the exhibits, to work on doing this in sort of the most arbitrary way possible. But the really important thing here is that this whole feedback loop has to happen fast compared to the dynamics, compared to the measurement time. Now, this is hard, but it's doable, especially because quantum coherence has gotten so long that we can just slow down the measurement. So I don't have data on this yet, but let me show you a simulation. So this is an extension of some work done by Lee Martin, our theory collaborator. What we can do is we can take two uncoupled qubits, and start them in a product state. So they're both in the plus x state. They're on the x-axis. And we want to generate entanglement from this without actually ever coupling the qubits. So this part right here is stuff that Lee did. What you do is you measure Z1 plus Z2. You measure the number of excitations in the system. This projects you to either the 0, 0 state, the 1, 1 state, or to the Bell state, 0, 1 plus 1, 0. And that's going to be our target. So what we do then is, as we're weakly measuring, we reconstruct this density matrix and feedback a drive on each qubit individually. We just drive them both with the same strength away from the states 0, 0, and 1, 1. If we see ourselves getting towards one of those states, we drive back away from it. What I'm showing here now is a trajectory simulation of a single run of this in simulation. And really it's just this purple curve you need to look at here. We start with 50%, so just completely the product state. And we're noisily, stochastically evolving this towards the target, towards the unit fidelity there. Again, this is a single run. This is not average dynamics. Now, the new thing that we, in my group, have added to this is like, okay, what if you want to get all the way there fast? What if you really want to get to the entanglement? Well, what you can do is get yourself most of the way there using this procedure, and then turn on a strong measurement along another axis. So this is now a strong full parity measurement along x, x1 times x2. Again, it has this Bell state as a measurement eigenstate. And so if we get close, we'll project with very high probability to the target state. And in this simulation, we're actually including dephasing. We're including decoherence, which would take our Bell state and flip it to the orthogonal Bell state, 0, 1, minus 1, 0. By having this strong measurement, we actually xenopin the system against this decoherence. And you can see it occasionally tries to get away and it gets pinned right back. There's no feedback involved in this. This is just the measurement. But then occasionally it really does escape, and then we turn on a feedback, which is just a pi pulse, to bring it back. Now this, again, is simulation, but it's simulated with real experimental parameters, about a microsecond delay time on the feedback, quantum efficiency of about 0.5, and we still get really excellent projection here. Now I'm getting told that I only have a couple minutes left, so I'm just going to throw the conclusions up here. I'm going to say that we're always hiring, so please come talk to me, and I'll take questions.
Thanks a lot. Questions right here.
Hi. Thank you. That was excellent. So I have a question about the cooling of the lossy environment.
Yeah.
So could you imagine characterizing this just by measuring the dephasing rate of a qubit? And if so, is that
that is exactly what we are intending to do. Okay. And the device and then here, if you zoom out, you'll see there's another qubit. Okay. And that qubit works fine. And the problem is that the dissipator is a little bit too good.
Okay, awesome. Thank you.
Okay, question all the way in the back.
Thank you a lot for your very nice talk, and you make this dissipation a friend. So I think it's very interesting, and I have a question in the first part of this. Markovian noise, then you get these fringes back. Mm-hmm. And we know that when we talk about this 50-50, it can be a superposition. That's true coherence, or it can be a mixed state, 0.5, 0.5. Yes. So I'm a little bit skeptical about this result. Is how you make sure it's a superposition state, not a mixed state?
So how do we make sure it's a superposition and not just a mixed state? Well, in simulation, it's super easy because we have access to the state. And in simulation, it is definitely a superposition. In experiment, we can do tomography. I don't have it here, but we do have a couple quick tests of tomography, and it really shows like it is in this case, still a superposition state. That's actually not ideal. What we really want for displaying this truly sort of non-Markovian environment is to go from your initial state to a mixed state and then recover that. So this is one situation in which the classical drive doesn't actually fully emulate the quantum environment, and we're with these more sophisticated techniques.
Okay, last question, Mike in the back.
Thanks, Eli. Great talk. Just again on this first part with the treatment using filter functions from about 9 years ago, where you can see the breakdown limits of the first order approximation and the like?
No, we have not. It's on the to-do list. In fact, we're going to talk about that later. But yeah, in some there's a pretty strong correspondence between this technique and something like dynamical decoupling. And just like you can use filter functions and dynamical decoupling to really analyze what's going on in your system, it should be possible in this technique.
Okay, let's thank Eli again. Okay, and the final talk of this session is from Peter Zapletal from University of Erlangen-Nuremberg, and the title is error-tolerant quantum convolutional neural networks for the recognition of symmetry-protected topological phases on noisy quantum computers. Thank you.
All right, thanks. Okay, thank you very much for the kind introduction. And also, I would like to start with a big thank to the organizers for setting up this very nice conference. It's been a lot of fun so far. And also thanks for giving me the opportunity to present our work here, which I've done together with Michael Hartmann and Nathan McMahon. All right, so I will jump straight to it. I would like to start with a brief introduction of quantum machine learning, which aims to use quantum computers to process large data and recognize patterns in them, and in particular in situations where you can't do it on classical computers. And this is a promising application for near-term quantum computers, as this can run with relatively shallow circuits and at a moderate level of noise. So in particular, what we are thinking about is using variational quantum algorithms, which are based on parameterized quantum circuits, which implement a unitary that depends on externally tunable parameters theta. And then to perform a certain task, we define a cost function, which could be an expectation value of a Hamiltonian, which we measure at the end of the circuit. And then then we use a classical optimizer, as for example, a gradient descent, to update the parameters theta, and in this way iterate this loop and move towards the minimum of the cost function. Okay, and so one could now think about processing classical data with this algorithm. However, there is a major bottleneck in doing that, and that's encoding of the classical data into the algorithm. One could, for example, starting from a product state, one could pass the. Okay, this is not rendered properly, but yeah. So starting from a product state, one could pass the classical data as sum of the parameters theta, or one could pass them as some parameters of the cost function. However, this is usually inefficient. So much more straightforward application for this is for quantum data, which are states that are prepared on a quantum computer. And now these can be directly fed into the parameterized quantum circuit without any need of encoding. So it's very native to this type of a problem. And then what we want to do is we want to now train this variational algorithm to identify characteristics of the input states, of the quantum data, and then use them as characterization tools for the quantum hardware, and then give feedback to the development of next generation hardware, and also to development of algorithms. So in particular, we consider here quantum phase recognition. So using the quantum machine learning for quantum phase recognition, which is a task given a quantum state. We want to determine into which quantum phase it belongs. And in general, this is not an easy task, especially if we have topological phases which have no local order parameters that we could use to identify the phases, and other characteristic quantities such as fidelity and entanglement are hard to access in experiments. Examples of such phases are symmetry-protected topological phases in one-dimensional systems, and intrinsic topological order in higher dimensions. Such phases have been implemented recently, have been realized on quantum computers, in particular using exact matrix product state representations of symmetry-protected topological phases, and a short quantum circuit to prepare a ground state of a surface code. There's been another experiment which used a variational preparation of the SPT phases, and I'm going to talk a little bit more about it later. Okay, so now once we prepare the state on a quantum computer, now we want to detect into which phase it belongs, and to that end, we use so-called quantum convolutional neural networks. This is a concept which has been put forward by Michel Lukin group, and it is based on a parameterized quantum circuit, which is analogous to classical convolutional neural networks, hence the name. And it consists of convolutional layers and pooling layers. In convolutional layers, we implement a translationally invariant unitary, and in pooling layers, we measure fraction of the qubits and reduce the system size by doing that. Such that after sufficiently many convolutional and pooling layers, we compress the information about some characteristics of the input state into a few qubits. Then we implement a general unitary in a fully connected layer and read out a single qubit, which labels the phase. And so this now network has been shown to detect SPT phases with a reduced sample complexity compared to the measurement of non-local order parameters. So in particular, what we consider here is a cluster Ising model, which is based on this Hamiltonian, which involves ZXZ stabilizer elements, as well as Pauli X terms and XX interactions. This Hamiltonian has two symmetries, and it exhibits a Z2Z2 symmetry-protected topological phase, as well as two topologically trivial phases, paramagnetic phase and an antiferromagnetic phase. Okay, so now we could use the QCNN, the quantum convolutional neural network, and train it, for example, using supervised learning to detect this phase. However, there has been also another concept also put forward by Michel Lukin group, which allows us to analytically derive an optimal circuit which detects the phase. And it's based on multi-scale entanglement renormalization ansatz, which is a tensor network which can represent states with long-range entanglement and thus also critical systems. So now I'm going to walk you through some of the derivation of how we designed the QCNN here. So in the procedure, we first identify a characteristic state that belongs to the SPT phase. In our case, that's the ground state when we have only the stabilizer elements, the ZX Z terms, and no X and XX interactions. The ground state is a so-called cluster state, and it's a stabilizer state. And so now we design we construct the QCNN in the following way. We first implement a unitary that maps the cluster state onto a product state. And then we implement the inverse of this unitary, preparing again a cluster state, but now on a reduced, now basically only on a sublattice of the qubits, such that after measuring the remaining qubits in the pooling layer, we obtain a cluster state of reduced system size. And such that then, basically what we do is we implement disentangling unitaries and entangling unitaries, then we do some kind of coarse graining, reducing the system size, while keeping the characteristics of the cluster state. So in this sense, we can really compress it into a few qubits. And then, actually, if we ran now the circuit in the other direction, in the reverse direction, feeding in state 0 into all qubits that have been measured in the QCNN, you would get a circuit that prepares us the cluster state. And this circuit corresponds to the Mera tensor network, right? So that's how it comes in here. And this allows us now here, basically, so in this way we embedded the cluster state, the characteristic state, into our QCNN. And now the next thing which we want to do is that we want to make all other states in the SPT phase flow towards the cluster state as we do the renormalization steps. So to this end, we want to detect perturbations that bring us from the cluster state to other states in the phase, which are here in the X Pauli X perturbations and XX perturbations. And then we detect them and correct them with a procedure which is analogous to quantum error correction. So we implement some gates, we measure some of the qubits and implement a gate that is gates that are conditioned on the measurement outcome. That's in quantum error correction. And this now allows us to make really all the states in the SPT phase to flow towards the cluster state, the characteristic state here. Okay, and so now where our contributions come in is that we now want to make this procedure robust to noise. When we prepare the input states on a quantum computer, there will be noise due to state preparation errors, due to decoherence and gate infidelities. We model this in our theoretical work by this error channel that acts with Krauss operators on the exact ground state. In particular, we consider X, Y, and Z errors. And as Amy was very nicely introducing possible type of noises earlier in this session, here, if we set all the probabilities of all the X, Y, and Z errors to be equal, we obtain the depolarizing channel, which captures quite well the characteristics of noise on NISQ computers. So now in our simulations, we use the MRG to find numerically exact ground states, and then we pull them through this error channel and feed them into the QCNN. So now, if we have Pauli X errors, they are actually here corrected for free by design of the QCNN. So as I was telling earlier, we have a sequence which is analogous to quantum error correction to detect and remove Pauli X perturbations. And it actually corrects both coherent perturbations, which are due to states being somewhere else in the SPT phase, not in the cluster state, or also incoherent perturbations or incoherent errors, which happen during the state preparation. So that's for free. Now, for Pauli Z errors, we need to try harder, but we can correct them by adjusting the quantum error correction sequence in the QCNN. And then what we do is that we basically stagger layers that correct X errors and Z errors, and then as we run the QCNN, we alternate these two types of layers. Okay, and here are our results. So here I plot the QCNN output for different depths of the QCNN on a cut through the phase diagram. And we can see that in the SPT phase, the QCNN output converges to unity, and outside of the SPT phase, it converges to 0. And so now this step-like function has several advantages for recognizing the SPT phase as compared to the direct measurement of the non-local order parameters, which here are the string order parameters. They are these Pauli strings. And now for a macroscopic length of these Pauli strings, they have non-vanishing expectation values only in the SPT phase, and they vanish outside. However, they vanish at the phase boundary, such that if we are close to it, we have a large sample complexity, which now complicates the recognition. On the other hand, the QCNN, we either have values close to 1 or to 0, which are much easier to recognize, and this reduces the sample complexity. Even a more crucial difference is in the presence of noise. So here it's plotted for a depolarizing noise with strength 1.5%. And the step-like function or the step-like output of the QCNN is robust to this noise. On the other hand, the string order parameters, they rapidly vanish with increasing length. And remember, we need long string order parameters to detect the phase, such that we cannot use them here to even detect Whereas the QCNN allows us to do it, and it tolerates errors as long as they are below threshold. Okay, so then the situation is more complicated when we are close to the phase boundary. There, due to law of entanglement, actually, we see that when we have errors, the QCNN output actually decreases. However, we can still precisely detect the phase boundary if you look at the slope of the QCNN output, and we find a sharp dip at the precisely located at the phase boundary. Again, string order parameters cannot be used because they vanish everywhere. Also, their slope vanishes everywhere, and we don't see anything. Okay, so for the sake of time, I'm just going to briefly mention that the QCNN circuit, which is logarithmic in the system size, is actually equivalent to a constant depth circuit, which just implements 2 layers of CZ gates, measurement of all the qubits in Pauli X bases, and then all the remaining processing can be done on a classical computer in post-processing. So, and this allows us to determine the QCNN output with the same sample complexity as the QCNN, but now drastically reducing the circuit depth. And this actually now allows the implementation of QCNNs on current hardware, which has been done in the group of Andreas Wallraff. The main contribution has been done by Johannes Hermann, Sergei Lima, Ans Rem, and Christopher Eichler. And we provided theory input in this work. So in this experiment, a variational sequence, so-called variational quantum eigensolver, has been used to prepare approximate ground states of the clusterizing model, and they are fed into a QCNN. And here we see results for 7 qubit experiment where we see that the QCNN detects the SPT phase with a larger fidelity than the direct measurement of string order parameters, demonstrating its robustness against noise. And this is despite the fact that the QCNN consists of finite fidelity gates itself. Okay, and with that, I would like to conclude. So I've shown you that we can design QCNNs that are robust against noise, and that we can use them to precisely detect phase boundaries. We also tested it for different SPT phases of generalized clusterizing models. I mentioned that we showed that you can reduce drastically the depth of the QCNN by using classical post-processing. And in future, we would like to design and train QCNNs, especially in situations where the phases are more complicated, such as intrinsic topological order or quantum spin liquids or anionic chains. And with that, I would like to thank you for your attention.
Thanks, Peter. We have time for 1 or 2 questions, please. Yeah.
Hi, Peter. Thank you very much for this very nice talk. I have a question about this phase transition. We know phase transition does not happen in any finite system.
Yeah.
And it's very clear you see some jump. But to actually see its phase transition, you may want to measure some order parameter or something. Did that done in this experiment or no?
So you're asking about the experiment. Okay, so that experiment was restricted to 7 qubits. So obviously we see there rather a crossover between 2 phases. Yeah. So in the experiment we really focused on basically on the robustness against noise, which we can already see for 7 qubits. Obviously, we have large finite size effects. You don't see really sharp phase transition. That's for sure. Yeah.
Okay, well, if there are no further questions, let's thank Peter and also all speakers from this session again. Thank you.
I just have the honor to now announce the coffee break that's supported by Keysight, so please join Keysight for the coffee break. We'll be here again in 20 minutes for the next session, and kindly ask the speakers of the next session to check by with me here in the coffee break. And then enjoy the time, look around the booths and see what's happening there. Thank you. Okay. I hope you all enjoyed the coffee break. I just wanted to make a little announcement about the venue itself. So on your map, you can see those blue areas. They are intended for networking, hangout. So please also use them. They are probably kind of hidden, but check them out. In one of those rooms, we'll actually have the beer break later. So you better find out soon where they are located. In the meantime, we're going back to our next session, which is the session on non-computing applications of superconducting qubits. And for that, I would like to hand over to Matti Silveri from University of Oulu. But I think the system just got stuck, so.
All right, welcome on my behalf also back from the coffee break. And like I said, this is the second session of today. And what we are going to discuss or hear today is about different applications of qubits, like how to study phase transitions in many-body physics, heat engines, sensing, things like that. We have 3 talks, about 20 minutes of each. And maybe I can introduce the first speaker. So the first speaker is Shiro Saito from NTT Basic Research Laboratories, Japan, with the title Detection of High-Frequency Defects in Superconducting Qubits. So, please.
I'll be right with you. So, here, this is for you already. One quick moment. So you're now good to go. The next slide is yours.
Okay, thank you, Chairman. Good morning, everyone. My name is Shiro Saito from NTT Basic Research Laboratories. And first of all, I'd like to thank Mikko and organizers for giving me this opportunity to talk our recent result in this nice and well-organized conference. And the title of my talk is Detection of High-Frequency Defects in Superconducting Qubits. And this work undertaken in collaboration with these people, and especially Leonid did the most of the experiment. And this work also supported by Crest JST and Moonshot JST. Okay, this is the contents of my talk. I'd like to start with a brief introduction about two-level systems defect in a superconducting circuit. Then I will show you our experimental result. First, we prepared the 3D C-shunt flux qubit. And by using this flux qubit, we detect high-frequency two-level system defects by using a spin-locking method. And finally, we succeeded in identifying the two-level system defects caused by charge fluctuation and critical current fluctuations. Then I will summarize my talk. There are many candidates for the two-level systems and defects in amorphous materials, which cause qubit decoherence. And for example, trapped electron states or tunneling atoms, dangling bonds, and so on. And especially low-frequency TLS defects cause qubit dephasing, and they are detected by qubit Ramsey measurement and spin echo, CPMZ, and spin locking. And on the other hand, high-frequency TLS defects cause qubit energy relaxation, and they are detected by the qubit spectrum and qubit T1 measurement, AC stroke measurement, and spin locking measurement, and so on. And this figure represents a Josephson junction. However, the two-level system defects are located everywhere, in the amorphous in a Josephson junction, or on the thin film aluminum surface, or vicinity to the qubit, and so on. And the high-frequency two-level system defects are observed in the qubit spectrum as an energy anti-crossing, like this, when the coupling between qubit and two-level system are strong enough. And this is an example of phase qubit. On the other hand, when the coupling between them is weak, then we cannot observe any signal from the two-level system defect in the qubit spectrum like this. However, we can clearly observe the two-level system defect as an increase of the qubit energy relaxation rate like this. And this is an example of X-mon. And these methods require qubit frequency tunability. And to solve this problem, we utilize the spin locking method to detect high frequency two-level system defect. Okay, let's move on to our experiment. Our qubit is a 3D capacitively shunted flux qubit. And to improve the coherence time of the qubit, we combine the 3D cavity and a capacitively shunted flux qubit. And this is a qubit loop, and those are the antenna parts. And we fabricated a capacitively shunted qubit on the sapphire substrate and put it on the copper cavity like this. And we apply the external magnetic field from the outside the copper cavity. And this 3D cavity provides a very clean environment of the qubit. And therefore, it is suitable to detect the high-frequency TLS defect. And cavity frequency and qubit frequency are well separated like this. So there is no spurious resonance around the qubit frequency. Therefore, we can detect high-frequency TLS defect around the qubit frequency. And this slide shows our qubit coherence time. And we measure the coherence time at the optimal point here. The best energy relaxation time of 90 microseconds. And T2 Ramsey was 30 microseconds, and T2 Echo was 130 microseconds. And we will this flux qubit to detect the high-frequency TLS defect. And thanks to clear environment of the qubit provided by the 3D cavity, and there is no energy anti-crossing in the qubit spectrum like this. However, we can clearly observe the two-level system defects as a reduction of the qubit T1 time like this. And in the next experiment, we will detect this two-level system by using the spin locking method. Then during spin locking experiment, first we apply the minus pi over 2 y pulse to the flux qubit to prepare the qubit is in a superposition state between ground and excited state like this. Then we apply the x pulse to the qubit to fix the qubit state in the x direction. And this pulse is a spin locking pulse. And during this spin locking pulse, the qubit state decoheres like this. And then we apply minus pi over 2 pulse again, and then read out the qubit population in the excited state. And we call this sequence as a sequence 1. And in the same manner, we can perform the sequence 2. In the sequence 2, we apply the plus pi over 2 y pulses here and there. Then final state of the qubit is the opposite direction like this compared to the sequence 1 here. And during spin locking pulse, the expectation value of the sigma x decays like this for the sequence 1 and like that for the sequence 2. And they converge to the 0. And this is a Hamiltonian of the system in laboratory frame, and qubit Hamiltonian and spin locking pulse. And in the rotating frame, the Hamiltonian is written like this. During this spin locking pulse, the qubit is in a dressed state, which are separated by the Rabi frequency of the spin locking pulse, omega r, like this. Then we introduce a two-level system. Let's assume the coupling between TLS and qubit is a transversal coupling. Then the system Hamiltonian is written like this. And qubit Hamiltonian and TLS Hamiltonian are represented by the sigma z, and the coupling term is a sigma x, and this is a spin locking pulse. When the Rabi frequency of the spin locking pulse, omega r, corresponds to the difference between TLS frequency and qubit frequency, the resonance condition is satisfied. And this is the resonance condition in the case of the positive detuning. Namely, the two-level system frequency is larger than the qubit frequency. On the other hand, this is the resonance condition in the case of negative detuning. And for both detuning cases, qubit state decays very quickly like this or like that, compared to the case without two-level system here. Interestingly, in the case of positive detuning case, the qubit state converges to the negative value. And in the case of the negative detuning, the qubit state converges to the positive state. This means that under the rotating wave approximation, the positive detuning two-level system works as a cold system, and negative detuned two-level system works as a hot system. And in this way, we can detect the high-frequency two-level system thanks to the Rabi oscillation of the spin-locking pulse without tuning the qubit frequency. Furthermore, we can judge the polarity of the detuning of the two-level system by checking the polarity of the expectation value of sigma x here or there. And this is experimental result. And here we plot the probability in the qubit excited state as a function of Rabi frequency of the spin-locking pulse and spin-locking pulse duration for sequence 1 and sequence 2. And as you can see, the qubit state decays very quickly at several Rabi frequencies here, or here, and here, and so on. And the right graph shows the cross-section of at the TLSC. And from these curves, we know the TLSC has a positive detuning. And bottom graph shows the two-level system defects observed by the spin-locking measurement and T1 measurement. Also, the TLS frequency changes in time. These three experiments shows a very good agreement. And by using the T1 measurement, we observe only positively detuned two-level system here. And by using the spin-locking measurement here and there, we can observe both positively and negatively detuned two-level system from here to there. And we can apply this method to the so-called fixed frequency transmon without frequency tunability. So I think the spin-locking is a very strong method to detect the high-frequency TLS defect. Now, okay, and so far, we fixed the qubit frequency, and we changed the pulse length. And in next experiment, we fix the pulse length and change the qubit frequency to observe the two-level system spectrum. And here, we fix the spin-locking pulse length at the 60 microsecond. And then change the Rabi frequency of the spin-locking pulse, and also we change the magnetic flux through the qubit loop to tune the qubit frequency. In this two-level system spectrum, we found the two types of two-level system defects. They are shown in the different curvatures. And the first type of two-level system shows the same curvature as a qubit spectrum, like this one, and that one. And this means that the resonance condition is written like this. And this is the same condition I explained before. And the second type of two-level system shows twice the curvature of the qubit spectrum, this one and that one. And this means that the resonance condition is written like this. And here, the qubit frequency is replaced by the 2 times qubit frequencies. And this means this indicates the coupling between qubit and two-level system is nonlinear. So to find out the origin of the two-level systems, we consider the coupling term in the Hamiltonian. And this is the flux qubit Hamiltonian, charging energy and Josephson energy of the typical junctions and alpha junction. And to include the effect of the two-level system caused by the charge fluctuations, we replace the charge operator by this formula. Then the coupling term written like this. And by using the ladder operators, we can write the coupling term like this. And this is a linear coupling. And to include the effect of the two-level system caused by the critical current fluctuation, we replace the critical current by this formula. Then finally, the coupling term is written like this. And now the nonlinear coupling appears. So in this way, we can identify the two-level system caused by the charge fluctuation and critical fluctuation by checking whether the coupling is linear or nonlinear. To conclude this experiment, we successfully identified the two-level defects coupled to the qubit due to the charge fluctuation and critical current fluctuation. The two-level system from 1 to 3 has the same curvature as a qubit spectrum. It comes from the charge fluctuation. And the two-level system from 4 to 5 has twice the curvature of the qubit spectrum. It comes from the critical current fluctuation. Okay, let me summarize my talk. I showed the 3D capacitively shunted flux qubit and two-level system defect detected by the spin locking measurement. And also, I showed the spectrum of the two-level system defects, which enable us to identify the critical current fluctuation and charge fluctuation. And as a future perspective, I think this method is useful to find the dynamic range of the fixed transmon operations. And also, we can feedback this result to the fabrication, and we can improve the qubit coherence. Okay, thank you very much for your attention.
All right, thank you very much for great talk. We have time for questions.
Hi. You had used the variation of T1, and you saw those dips where you identified them as coupling to TLS. But often one sees that T1 varies with time itself, right? Have you looked at how the stability of your T1 is at the good points? Is it of similar magnitude? Or
Okay,
you can identify these TLS suckouts a lot more clearly?
Yeah. Our time variation of our T1 is range like from 50 to 90 microseconds, this range. So obviously, these dips are beyond that range.
You don't see very big outliers as function of time?
No, yes.
One of the questions I would have is, what defines your maximum frequency range you can achieve in this method?
Okay, so far, our radio frequency is up to about 80 megahertz. So we can detect the from minus 80 megahertz to up to 80 megahertz. But if we can increase the microwave power, then we can sweep larger range. So it depends on the microwave power.
There was a question in the back. Thank you.
Yeah, thank you very much for the excellent talk. I'm wondering how repeatable are those different TLS spectra? So was it something measured? So we have this identified 4 distinct families of TLS defects. How repeatable are they? For example, if you measure on another, as a tool, it's really useful. But I mean, is it something? Is there a trend going on, or it was like the hero device that you observed?
Okay, thank you. During the single cool down, this two-level system is reproducible. But after thermal cycling, the position is changed. So, for example, we observe this two-level system spectrum, and to check this two-level system is a charge fluctuation, we try to apply the in-plane magnetic field and repeat the same spectrum, and then this spectrum reproduced. So, yeah, during the single cool down, this spectrum is reproducible.
We have time for one question, and let's take here the last one.
Thank you very much for the very nice talk. So you identified these 2 different sources for TLS. I was wondering whether you have investigated whether temperature may influence them in a similar way.
Sorry, temperature dependence of the...
Yes.
Okay, unfortunately, we didn't take the temperature dependence. So, I'm sorry, I have no idea about the temperature dependence. Yes.
All right, let's thank the speaker and the questions likewise.
Thank you.
And the second speaker is Andrew Guthrie from Aalto University, and the title is A Cooper box coupled to 2 resonators and architecture to a quantum refrigerator. Please.
This work? Yeah, so thanks to the chair and thanks to the organizers for giving me a chance to speak today. So my name's Andrew Guthrie. and I'm going to be telling you about some of our recent experiments towards realizing a quantum refrigerator in a superconducting circuit using a charged qubit. So this work was done while I was a postdoc at Aalto University with Professor Jukka Pekkala. Although as of last week, I've joined IQM. So this is now being carried on by the other members of the Pico group. So our goal in the Pico group was to study the fundamental limits of thermodynamics using superconducting circuits. And what that means in reality is normally to take some, quantum system, maybe that could be a qubit or qubit or something else, and embed that between a system of heat baths, for example, this hot bath and cold bath. And then what we do is we study the heat flow through that quantum system and try to see what that can tell us about the nature of heat and work at a fundamental level in quantum systems. And do the laws of thermodynamics ever, is it possible to ever say something about the laws of thermodynamics at the fundamental level? Or a slightly more realistic depiction is what's on the right here. So we have a superconducting qubit, then coupled to two superconducting resonators, which are then terminated by these heat baths. So this is kind of more like the real system which we would study. So we realize these heat baths by using adding normal metal elements to the superconducting circuits. So that could be here a piece of copper, which adds dissipation. And then to that copper, we can add superconducting probes. And you can see from the current bias, if you connect a superconducting probe through an insulating barrier to a piece of normal metal, you can effectively measure the temperature just by measuring the IV curve. So that IV curve becomes sensitive to the temperature. And then by connecting more than one probe, you can basically control the temperature and measure the temperature of this normal metal island. So this is effectively how we realize heat baths in our system. And importantly, this probes the electron temperature of the normal metal and is not the temperature of the superconductor. And then we couple that with superconducting qubits of various types. So on the top, you can see a transmon qubit, Exmon type fabricated in our group. And below, you can see a charged qubit, which is what I'm going to be focusing on today. So our first kind of experimental foray into this type of experiment was this tunable photonic heat valve. So what we did was we took a transmon type qubit and coupled it to two lambda by 4 resonators of the same frequency. And then by changing the flux on the qubit, you can either bring the qubit into or out of resonance with this circuit. And we have this hot bath and cold bath, which is exactly what I showed before. So these are normal metal resistors, copper resistors, which short the lambda by 4 resonator to the ground. And so by using the superconducting probes, we can change the temperature of the heat baths and study how the photons flow through this circuit. And what we see is that, as you'd expect, when you bring the qubit into resonance with the circuit, which happens twice per flux quantum, the photonic heat power flowing from the hot bath to the cold bath increases. So that happens twice per cycle. So what's happening is that the flux changes the qubit frequency, and then the qubit is either in resonance or out of resonance with the circuit. And that's published in this Nature Physics paper here. We can go one step further, and then if we take the two lambda by 4 resonators and make them different frequencies, we now introduce kind of nonlinearity into the system. So because you have this nonlinear microwave element in the center, which is the transmon qubit, and then you have these unequal resonances, this circuit is now non-reciprocal. So we have a heat bath on the left side again, and a heat bath on the right side, so which is our hot bath and cold bath. And what you actually find if you study this system is that the heat flow from the left side to the right side is not the same as the heat flow from the right side to the left side, even if you make them the same temperature. And that's shown in this purple curve, which is the flow from this side to that side at the same temperature, and then the green curve is the flow from the right side to the left side for the same temperature. And this is what we call heat rectification in a superconducting circuit. But we now want to move from this kind of DC heat transport, which I've shown you before, where we're just measuring, we're just keeping the qubit at a fixed flux. We want to move to this kind of like active regime, where we can realize heat engines and refrigerators. So what happens is that we can change the flux or change the qubit frequency in some periodic way and use that to realize quantum Otto refrigerator in this case. So the Otto cycle consists of 4 strokes. We start off here with the qubit population determined by the temperature of the hot bath. We then go through a adiabatic stroke where we change the qubit frequency from the hot resonator frequency to the cold resonator frequency. That's the adiabatic stroke. Then we allow the qubit to thermalize with the cold bath. So the qubit population is then determined by the cold bath, and then we perform one more adiabatic stroke back to the frequency of the hot bath, where the qubit can again thermalize. And what you find if you study this system mathematically is that if you choose the frequencies of these resonators, so the 2 resonators, such that the ratio is larger than the ratio of the temperatures, you effectively realize a refrigerator in this case. So if you drive the system fast enough, you can effectively pump heat from the cold bath to the hot bath, achieving refrigeration. So until now, I've spoken about a transmon qubit, which has the small EC-EJ ratio. But for these experiments carrying on, we used a Cooper pair bot, so effectively a charged qubit. And that's sort of the simplest kind of qubit you can make. It's just a superconducting island with a Josephson junction and some capacitance to ground. And then you choose the parameters such that the EC is high by making the island very small. And in that way, it does have some advantages over the transmon qubit for this purpose. To use a transmon qubit for this purpose has the disadvantage of small anharmonicity and typically negative anharmonicity. And that means that we cannot really isolate a 2-level system in the transmon qubit in this case. And we find that the higher energy levels are very easily excited by the hot baths. If we want to realize a refrigerator, we need a well-isolated 2-level system. Another advantage of using the charged qubit is that you can control the frequency in using gate voltage rather than using a magnetic flux, which means we can apply much smaller signals to the chip and makes our experiments more sensitive. There are some disadvantages that come with using a charged qubit, and we'll see some of those later, which I'm sure you're all aware of. So before we fabricate sort of our real refrigerator device with the heat baths, we first fabricate what we call a spectroscopy sample. So this is all superconducting, and we have a microwave feed line, which allows us to probe our system. And here are our 2 resonators, so a low-frequency resonator and a high-frequency resonator. So this one is at around 4.7, and this one is at around 8. And then our superconducting qubit, sorry, it's not so easy to see here, just very simple, just consists of a straight line, which is the superconducting island, and a single Josephson junction to ground. So really the simplest kind of Cooper pair bots you can fabricate. And then we have a gate line, which allows us to change the frequency of the qubit. And then we have some additional filtering here to stop the qubit decaying to the gate line and to stop the resonators decaying to the gate line. And if we measure the spectrum through this feed line, we can clearly identify the 2 resonances at 4.7 and 8. And the reason that we first make this spectroscopy sample rather than the real refrigerator sample is that, I think it was mentioned in the previous session also, that when you try to probe resonances with lossy elements on the chip, the dissipation can be too high and you can't probe the system. So if you want to do this like 1-tone, 2-tone spectroscopy experiments, it makes sense to do it in a system with no lossy elements, and then you can add the lossy elements later. So now we can see that it works. If we change the gate voltage coming from here, we can identify our 2 avoided crossings, one with the high-frequency resonator here, and then these are measured at the same time, and then you see the avoided crossing with the low-frequency resonator. And we've achieved our goal of having high coupling with both, and the EC ratio is, EC is larger than EJ, so we're really in this Cooper pair bots limit rather than the transmon limit. Now I come to a couple of the disadvantages of using the Cooper pair bots. One is about sensitivity to island parity. So in the Cooper pair bots, whether you have one quasi-particle on the island or no quasi-particles on the island will actually change the frequency, and it will change the frequency by quite a lot. So we sometimes see some leftover resonance signal here, and that's effectively caused by the qubit some of the time you're measuring being off resonance because of a quasi-particle on the island. So that will effectively slightly decrease the cooling power of the refrigerator, but actually not significantly. And then if we measure the 2-tone spectroscopy, we can get the dissipation so the dephasing rate of the qubit to be 24 megahertz, which is kind of very, very high compared to typical trans-1 qubits and stuff, but actually for the operation of the refrigerator doesn't significantly affect. I'll discuss that in a second. Actually, we can even operate the Cooper pair bots as a quasi-particle detector. So if we sit on the resonance, say at 8 gigahertz, and measure very quickly, you can see what I was talking about, that you see these switching between the odd and even parity on a fast time. So actually, our refrigerator will only be operating when we're in the right parity, and the rest of the time, you won't get any refrigeration. So now that we have all the parameters of our circuit, we can basically study our system numerically. And we do that using the Lindblad master equation. So we have the unitary operation of the qubit, and then we have two dissipators corresponding to the two heat baths. And the form of the heat baths basically takes a Lorentzian form, and then this Boltzmann distribution corresponding to the temperature of the baths. And if you do that, inputting all of our parameters from the coupling we extracted from the singletone data, we can see that we predict to have almost 100 attawatts of cooling power, and then correspondingly cooling. So once you're driving the system at a few gigahertz, you have quite significant cooling power. So we really expect these devices to work. And importantly, from the previous slide, you can see that the quasi-particle switching rate is kind of the order of 500 microseconds. And from the previous slide, again, we see that the dephasing rate was around 24 megahertz. But the operation rate of our refrigerator is in the gigahertz regime. So actually, this quasi-particle switching and dephasing doesn't significantly impact, because those rates are much slower than the operation frequency of the refrigerator. So now I can show you the real device, basically. So it's nominally identical to the previous device. You have a gate line, Cooper pair bots, couplers to the capacitive coupling to the two resonators, and a single junction to ground. But then we remove the feed line, and then we add these normal metal resistors. So these are copper, and then we connect 4 superconducting probes so that we can control and measure the temperature of each side. And here's the real device bonded in our sample holder. So we have the 4 connections to each side, and then wire bond around the outside, and then this is the gate line. So then effectively all the measurements are done in DC, so you're continuously monitoring the temperature of the baths while driving the gate line to see what happens. So first I can show what we saw when we didn't have any drive. So if we vary the amplitude of the gate, so we're effectively just changing the qubit frequency without any driving, we don't see any bid signals, which is what we would expect, because the qubit is never actually in resonance with this circuit. So this resonance is 8 gigahertz, this resonance is 4.7 gigahertz, and at no point is the qubit in resonance with both. So as we sweep through, we just see very, very weak modulation. So that was kind of expected. And then we can fascinatingly see what happens when we increase the amplitude of the driving signal. So this is where we can potentially expect to see some refrigeration in our circuit. For the quite high driving frequency, we can actually see, so this is the temperature of the hot bath, this is the temperature of the cold bath, and in a certain parameter regime, it really does seem like the cold bath is cooling, even by some quite large amount. And then correspondingly, at the same temperature, the hot bath is heating. So it does appear to be some refrigeration. What's a little bit confusing to us still is what causes this exact shape, and why we don't see, so if we sit on one of these features, we don't see the strong gate dependence that we would expect. So if you're changing the DC offset, you'd expect this feature to shift quite significantly, but it actually only shifts like a small amount. So that's still a little bit clear to us, but this is just still very early measurements, so these are still ongoing. Yeah, so get to the outlook. So we have some, the measurements of the first generation are ongoing. It's really exciting, but we're not clear to me why we can have frequency-dependent cooling without the gate dependence. But it does seem like we see some cooling, which is already like very exciting. And we should try to understand better what the role of the quasi-particles really is in this engine operation. So in the next device, we're making the coupling stronger and trying to further engineer to improve this quasi-particle parity and improve the sensitivity of the thermometers to reduce our noise. So yeah, thanks everyone for listening. this is a recent photo of the Pico group from Nutzio, which is just a national park not far from here. So I'd like to thank Yuka for his support, and Christoforos Dinos Satria, who's the PhD student on this project, and Ilari Makinen, and Yu Chen Chan, who's a postdoc in this project. So thank you.
Thank you for the clear talk, and thank you for keeping time. So we have time for questions now. So the first one is there.
Hi, and thanks for the nice talk. It was interesting. My question is, I don't think you mentioned it, but I might have missed it, but about the potential applications there. Because I suppose you couldn't cool something as big as a mixing chamber plate, but maybe some neighboring chips, or like what are you thinking of applications for this kind of refrigerator?
Yeah, I suppose the main motivation to study this kind of systems is related to sorts of fundamental physics, like understanding this open quantum systems and like how we can apply that. As far as like technical applications, you could imagine to, since the cooling power is of the order of kind of less than a femtowatt, you could imagine to embed this kind of system inside a superconducting qubit and cool the resonators or cool the qubits down to the ground state if you wanted to, because the operation time is very fast. If you're driving of the order of a gigahertz, then you can actually extract 100 attawatts of cooling power. You could effectively cool a qubit to the ground state in just 10 nanoseconds or something.
Thanks.
I'm wondering if the cooling of the device couples to all of the different energy exchange mechanisms equally, like because as you go down, different mechanisms hold the heat. Do you expect that eventually you won't be able to cool with this device, or is it, what mechanism is currently dominant on the heat exchange?
You mean like at what temperature would this technique stop working? Kind of?
Yeah, because like not all energy is of course the same.
Yeah, so I mean this is photonic cooling. So we're kind of most effective in the temperature regime, kind of like 200 to 400 milli-K. And if you try to push the system much below that, then the photon populations become very, very low, and you effectively can't. The qubit population becomes very small, and the cooling becomes really ineffective. Yeah.
Thanks.
Yes. A question. So these temperatures that you've been talking about, they are photon temperatures, right?
Yeah, that's right.
I just noticed that the
sorry. It's electron temperature, but the heat transport mechanism is photons.
Ah, okay. Because yeah, then maybe my question is not relevant.
Yeah, sorry. Yeah, that was confusingly explained.
All right, we have time for one question. Where is the last one? They're back.
Hey, thanks. Thanks for the talk. So my question is about the scalability of this. Can you actually put more of these in parallel to your qubit, or how does it work? Can you scale the cooling power easily?
That's a good question. It's not something I've really thought about. Yeah, I think it's entirely feasible that you could couple one heat bath to multiple resonators and therefore increase the cooling power that way. Or just have an array of qubits which are kind of operating all in. But it would be difficult with charged qubits because you do suffer with charge offsets. So kind of we operate one device for about an hour and then we have to sort of calibrate the charge. So you would be like continuously doing that for all of the different qubits to keep them synchronized. But yeah, it's an interesting question. It's definitely something to think about.
All right, thank you, and let's thank the speaker and the discussion. All right, then the next speaker is should be Soham Mukhopadhyay from Institute of Science and Technology, Austria, with the title Thermally Activated Superconductivity in Insulating Josephson Junctions. Please.
Thank you for the introduction. Hi, I'm Soham. I'm a PhD candidate with Professor Andrew Higginbotham at IST Austria. Before I begin, I'd like to thank the organizers for giving me this opportunity to present our work in this conference. Today I'll be talking about superinductance for a melted insulator. And what I mean by that is I'll be talking about the superconducting insulator phase transition in a chain of Josephson junctions. Superconductivity is usually destroyed by heating. However, in some cases, it can also be broken down by purely quantum mechanical effects. Chain of Josephson junctions are model quantum minibody systems which can be tuned through an SIT. In a JJ chain, the two energy scales which are competing with each other are the Josephson energy EJ and the charging energy EC. Josephson energy tries to align the superconducting phase between two superconducting islands. Charging energy EC seeks to destroy it. The ratio between EJ and EC determines the ratio between the charge fluctuations and the phase fluctuations in the environment. As long as EJ is greater than EC, the charge fluctuations are greater than the phase fluctuations, and superconducting correlations are prevailed. When EC overwhelms EJ, the phase fluctuations are larger than the charge fluctuations, and superconducting correlations are lost, and the chain enters an insulating regime. Pioneering work in this field had been done by Professor David Haviland in early 2000, where he showed that we hit the SIT for longer JJ chains. This was followed by work of Professor Timothy Duty, where he established the insulating phase of these JJ chains as pin-Luttinger liquids. This was followed by work of Professor Vladimir Manucharyan, where he showed that in long insulating JJ chains, they can support high-quality microwave modes. Despite this amazing progress, the behavior of these JJ chains in the vicinity of SIT is unclear. This is where we begin. Our approach is to combine both microwave and transport measurement techniques to study the SIT. From microwave, we can measure the plasma modes, from which we can infer the microscopic parameters, such as the charging energy to ground EG and the Josephson energy EJ. On the transport side, we can measure the resistivity, from which we can infer the scaling behavior of the system and the phase diagram. So to start with microwave measurements, we have a JJ chain of 1220 Josephson junctions, which are capacitively coupled on either side, which helps us to do transmission measurements. When you measure the transmission of a weak probe tone while varying the frequency of a strong pump signal, we see sharp dips which correspond to the plasma modes of the system. These sharp dips are equally spaced at lower frequency, which reflects the speed of light in the chain and the length of the chain. Oh, thank you. As you go to higher frequencies, these modes are clumped together owing to their proximity to single junction plasma frequency. Now, we apply a magnetic field B parallel to the plane of the chip and perpendicular to the axis of the chain. And we extract the peak frequencies at all the magnetic fields. When you plot these peak frequencies with the mode number K at various magnetic fields, we have the dispersion curve at various magnetic fields. When you fit the dispersion relation for a JJ chain to this curve, we can infer the Josephson energy as a function of magnetic field and charging energy to ground. With these inferred parameters, we can calculate the Kg, the global superfluid stiffness, or the Luttinger parameter. So when you plot the Luttinger parameter with the magnetic field B, we obtain this experimental curve. The colors indicate the superconducting and insulating phases as predicted by theory. So microwave measurements indicate that for all the magnetic fields, our chain lies in the insulating regime as predicted by theory. On the transport side, we have another JJ chain with nominally similar number of Josephson junctions, which are galvanically coupled on either side. We set up standard 4-probe logging measurement techniques to measure the zero-bias differential resistivity of the chain. When we measure the rho, zero-bias differential resistivity, with lowering temperature, we see a precipitous drop in resistance by 3 orders of magnitude before saturating at a low value. This indicates that there are superconducting correlations still existent on the chain. So we have an apparent conflict here. While microwave measurements indicate that our chain is in the insulating regime as predicted by theory, transport measurements indicate that there are superconducting correlations existent on the chain. So we thought, well, let us repeat the same technique that we applied in the microwave side. We apply, again, a magnetic field B parallel to the plane of the chip and perpendicular to the axis of the chain. And we repeat and measure the zero bias differential resistivity while lowering temperature. And what you observe is that the precipitous drop in resistance is preserved at lower magnetic fields, while as you go to higher magnetic fields, the behavior is completely reversed, where initially the resistivity increases on lowering temperature before saturating at a very high value. So experiments indicate the SIT is somewhere between these two fields, somewhere here, where the behavior changes. And to compare with the phase diagram that I showed you earlier, it would be somewhere around here. Okay, just ignore this number, that's the page number. To potentially resolve this conflict, we propose this phase diagram. What I would like to draw your attention to this line, or this dotted line T-ins, this one, dotted line T-ins. T-ins is the temperature where the thermal length of the system matches the charge screening length. Above T-ins, for temperature above T-ins, the thermal length of the system is lower than the charge screening length, and short-range physics governs the system. In this limit, the SIT is controlled by Kc, the local superfluid stiffness. When temperature is lower than T-ins, the thermal length of the system is greater than the charge screening length, and long-range physics governs the system. In this limit, the SIT is controlled by Kg, the global superfluid stiffness. By the way, it is interesting to note that this limit is the one we are familiar with SIT. We assign the phase where we have short-range physics as the local superconductor LSC. And comparing our inferred parameters from both transport and micro measurements, we see that our Kg is very low, while our Kc is greater than 1. So basically, we are performing our temperature sweeps somewhere in this region. Theory predicts that the resistivity in this regime is related to temperature with this power law. A straightforward way to test the theory is to fit standard power law relation to the rho versus T curves that I showed you earlier. When you fit the power relation to these curves and extract the power and compare them with the local superfluid stiffness Kc inferred from microwave measurements, we see linear behavior with a slope close to pi and intercept close to -1. Again, if we compare the inferred amplitude from the power law fits with the Josephson energy J, we see good agreement of data with theory, where rho naught is the only free parameter here, and this is close to single junction normal state resistance. This gives strong evidence that there is local superconductivity on the chain. To understand the limits of this locally superconducting phase, we perform the same measurement over the whole BT parameter space. We set the temperature of the fridge and then vary the magnetic field while measuring the zero bias differential resistivity at all the points. When we do that, we observe that we have this dome of local superconductivity accompanied by wings of insulating phases. The difference, the resistivity between these two phases differ by 5 orders of magnitude. The red vertical lines indicate where pi Kc equals 1. This is the theoretical prediction. Based on this theoretical prediction, we observe big qualitative changes on the data. This gives very strong evidence that we have local superconductivity on the chain. Again, we can compare this data with theory, and we can recreate this locally superconducting dome from theory as well. For that, I again refer back to the power law relation that I showed you before, and we can plug in values of temperature and Kc to this expression. The upper limit of temperature in this case would be the plasma temperature of the system at various magnetic fields. And the lower limit of the temperature, which is the saturation that we observe in our curves, would be T-ins with a proportionality factor of 5. And when you do that, we can see that we can actually faithfully create this locally superconducting dome as observed in that experiment. The remaining thing to check is the crossover scaling, where our chain goes from locally superconducting to this insulating state. And for that, we extract the corner temperature T star from this data. And also, we may repeat the same measurement at the boundary between these two phases, the locally superconducting insulating phases. So we repeat the measurement here. And the plot on the right is plot of that measurement. And it's very interesting to note that as you go to higher magnetic fields, the behavior of rho versus T changes. And so on lowering temperature, initially we observe that rho decreases with temperature, and then it shoots up, where on decreasing temperature, rho goes up. Also, we extract the corner temperature T star from these plots. When we plot all of these extracted T star with magnetic field B, we observe that at the magnetic field B, where pi case equals 1, below that, T star decreases with B, and above that, T star increases with magnetic field B. Also, we can fit the data to the theory of the expression of T-ins that I showed you earlier, and we see reasonable agreement with theory. This again gives good evidence that the crossover from the locally superconductor to the saturation observed is actually crossover into an insulating phase. And so with that, I'd like to zoom out a bit. And so far, the data I've shown you is basically the measurement of the slope of this line, which is the zero bias differential resistivity. And if we zoom out a bit and bias our chain in wider bias, we see many current peaks accompanied with these apparent supercurrent features at zero bias. Now, if we apply a in-plane magnetic field B and keep on measuring these current peaks, we see them disappearing at near the SIT. So there are a lot more features to understand which we still don't know. For example, we don't understand the fine features on this curve. Also, these peaks are supposed to be spaced by twice the superconducting gap of aluminum, but they are actually not. And we still don't understand the envelope of this curve. This points out that we have barely scratched the surface, and there's still much more to be discovered. So to conclude, we understand where do superinductors lie on our phase diagram. So in the limit of the charging energy to ground much greater than the Josephson energy, greater than the charging energy of a junction, we have our superinductors lying in this area of the phase diagram. We also have the experimental phase diagram where we understand the limits of this local superconductor. And now we know why some quantum circuits which employ long JJ arrays work so well. They are at the sweet spot where the temperature is low enough for local superconducting correlations to prevail, but the temperature is large enough such that it's melted phase of an insulator. In short, the short-range superconducting correlations are stabilized by thermal decoherence. With that, I'd like to thank you for your attention. Andrew is the PI who led the whole work. These are all the people who are involved in the work. These are our funding agencies. And I'd like to thank the scientific service units of IST Austria. Thank you.
All right, thank you for the great talk. Time for questions.
It's a very nice talk.
Thank you.
In these 1D chains, you're applying a magnetic field to sort of tune things. Typically in studies of this in two-dimensional materials, there's this magnetic field tuned transition, but there's also a disordered tuned transition. Do you have a sense of whether the field is acting as field would in 2D, or is it acting more like disorder?
May I ask the question? I mean, you are asking if it's a disorder-induced transition or a field-induced transition?
Sort of, if you were to try to extend this to a 2D analogy for the 2D magnetic field, or 2D superconductor insulator transition.
Okay.
Is field in 1D sort of playing the role of field in 2D, or is it playing the role of disorder in 2D?
Oh, I don't know. I haven't thought about that, but thank you. I'll think about it. Okay.
Thanks. Next one. There.
I just have a quick question.
Yes.
Just the lowest temperature doesn't seem like the resistance is diverging. So is it a true insulating state? Or I guess another way to ask is, are you applying high enough of a magnetic field to drive it to an insulating state? Yeah, like this one.
You mean?
On the left-hand side. So the curve at the largest magnetic field.
Yeah.
Maybe the left figure.
This one, right?
The left figure.
Oh, this one.
Yeah,
oh,
that trace particularly.
Yep. Can you please repeat that question? Repeat your question again?
If it's insulating, I would assume that it's diverging at 0 temperature.
For an insulator, as you lower temperature, the resistivity would go up. So here, as you lower the temperature, it goes up and then saturates. I don't understand what do you mean by diverging.
What I meant is that at 0 temperature, it should be infinitely large.
Okay. So here, actually, it's this saturation is basically our lock-in saturating. So it saturates between very high values. So that's the value we measure. That's it. But you are right. Yes, it would go to infinity. Yeah.
Some more questions? They're back.
Hi, thanks for the nice presentation. Actually, my question relates to the first question, actually. So the curve, if you look at on the right-hand side, the resistivity increase is very classical as it happens in condo systems. So your resistivity kind of shows a dip, and afterwards it starts to increase. So this relates to, maybe you can think in this direction, and I don't know if you have already done that, that the insulating behavior starts with some sort of nucleation sites because of the magnetic field inducing these nucleation sites. And these points act as a center to trap the electrons and in order to increase the resistivity. So I don't know if it connects to the same, or could you comment on this?
I haven't thought about this as being the Kondo effect, but thank you. I don't. But thank you. That's a very useful comment. Yes.
Thanks.
All right. Thank you. We have time for one quick question or comment. Anybody here in front?
Oh.
This graph you showed at the end with the voltage spacing not equal to 2 times the gap. What is the spacing? And have you considered the effect of quasi-particle poisoning, maybe? Like why you might see one gap?
Sorry, what?
If the system was had significant quasi-particles, you might only see one gap in this structure, maybe.
I'll answer your first question.
Yeah.
So the spacing between the peaks is almost equals to 2 delta at like lower biases, but as you increase the bias, the spacing decreases. But the difference is of the order of few microvolts. Yep. And but can you please repeat your second?
I think you answered it.
Okay. All right. Okay.
All right. Let's thank the speaker
Thank
and
you.
all the other speakers.
Thank you.
Okay, the only thing left now is the lunch. So we have kind of this setup that we have 2 different lunch slots. In the meantime, I think it's great to explore the different booths that are out there in the area around this hall. I would like to thank also the session chairs and all the speakers of this first block in the morning. It was really great. You did a great job. And we have a little present for you. So if you stay here as the session chair or Andreas as a keynote speaker, please stay in front. And for the rest, enjoy the lunch, enjoy the booths, and see you again here at 2 for the poster session. And if you have your poster, be there 50 minutes before time, please. Thank you.
Those of you who are still outside, we're going to get started very soon, so please come and take your seats. It's great to be here at the conference, so let me thank Mikko and other organizers for putting together this wonderful conference. It's actually my first international trip in nearly 3 years, and still feeling weird about wearing the mask, not wearing the mask amongst so many people in close proximity. I was really hiding in my apartment for most of the pandemic. So it's good to be back and good to see a lot of familiar faces. This is a session, we have a keynote speaker first, and followed by a session on unconventional qubits with interesting names. So let's get started. The first talk is by Professor Vladimir Manucharyan, who's very recently moved from Maryland to Switzerland. So yay for Europe. And he's going to be telling you about their recent work and improvements in the Fluxonium qubit. And as I'm sure many of you know, the Fluxonium was invented by Vlad when he was a PhD student in Michel's group. So without further ado, let's hear about the new exciting things. Vlad, over to you.
Okay, hi everyone. Thanks, Vijay, for a nice introduction. And thank you, the organizers of SQA conference. See, I put it here. We're using the wrong slide, but you know, the logo is still here. For giving me the opportunity to speak. So I will. Yeah, I also should say that I'm not really sure if my material is all that keynote, but at least it was made in a keynote. But converted to PDF because it's a Windows computer here. So everyone got its share. Anyway, so I'm going to review the recent progress with Fluxonium qubits done at my lab at Maryland. So I'm at a PFL now, and this is a picture of my vanished group. So they all contributed to this work, and now they're all working at various exciting projects on quantum computing, but outside my lab. And I'd also like to thank all the agencies for sponsoring this work. So I was thinking yesterday that it's such a nice conference because everyone is in business, so you don't really need to make all these introductions about circuits and Josephson junctions. But I thought that I still, say something introductory. And I figured that I can talk about a periodic table of circuit atoms. So we think of superconducting circuits as atoms, and we give them funny names. More or less mimicking this, the chemists, but the way chemists organize their atoms, there's actually some science behind it, and I was thinking that maybe we can play the same game with the qubits. So to introduce my version of this kind of periodization, remember the charge qubit is basically a Cooper pair tunneling back and forth onto different islands. Cooper pair box. It was later, there was a contronium qubit that was a derivative of it, but it's basically a charge tunneling, right? That's the macroscopic quantum variable. So the Heisenberg uncertainty relation tells us that, well, there have to be a dual regime where there's a phase that is a pretty good quantum number that is established across the two superconductors. That's the Josephson effect, and this phase can vibrate, and that gives us the phase qubit and the transmon. So in case of a transmon, this crossover from the tunneling spectrum to the phase vibration spectrum was actually nicely worked out. So you all know about this. And anyway, so these are the two kind of types of atoms that deserve their own names. So the two different macroscopic quantum variables, it's the charge and the phase. So, but now, just like there's duality between electric and magnetic fields. There's also duality between charge and flux. To me, it's kind of the same, so I'm going to put Maxwell here, although I'm not too sure, but I'm pretty sure it's a classical thing. And so you get a flux qubit where you have a loop instead of islands, and this loop is interrupted by a junction. The flux can tunnel in and out. You can think of it as some particle, double well potential. There are usually some higher states that make the story more complicated, but if you only focus on low energy states, it really looks dual to charge tunneling. And so my talk today is focused on Fluxonium, which is actually nothing else but just an evolution of a flux qubit from shunting a small junction by 3 junctions to shunting it by, in this first case, it was, I think, 43 junctions, if I remember correctly. So that was one thing that made a big improvement. It's basically made an inductance of this loop so large that the flux noise that would offset the energy levels become kind of practically unimportant. The T2, due to flux noise, scales as the number of junctions squared. So you can imagine that, when you make 100 times more junctions, you're going to win 10 to the 4 times in protection. And that's pretty much why Fluxonium is so much easier to work with than a flux qubit. And then the other notion we introduced was capacitive coupling. At that time, it was weird to think of a flux qubit coupled capacitively, but we thought of this qubit more like a charge qubit that was shunted inductively, so it was okay to couple it capacitively. So now I think we understand that it's kind of silly to even think about the difference between capacitive and inductive coupling. Like in the end, you're just coupling an atom to a field, and just like field consists of electricity and magnetism simultaneously, so it kind of doesn't really matter how you couple it. But so in practice, it's much easier to do a capacitive coupling by analogy with transmons. So, and so before I proceed to kind of reporting on what we've figured out with Fluxoniums, I want to tease you a little bit with the fact that it looks like there is a 4th spot missing in this periodization. So there has to be something that is what a phase qubit is or transmon is to a Cooper per box. So as you make flux tunneling more and more intense across the loop, the flux quantization has to become washed out, and there has to be a different macroscopic quantum variable that kind of looks like phase, but it has to be charged. It should emerge, and the spot has been missing until recently. So, and it's now known as quasi-charged qubit. So, and it's really nothing else but a kind of a dual of a transmon. So I want to explain how it comes out. So you see, the reason there are only 4 spots in this table is because I limited to elementary circuit atoms such that there's only one variable. So you can only use an inductance, capacitance, and Josephson junction there, because if you add one more element, you're going to need more variables to describe it, and you're going to get a molecule rather than an atom. And so to figure out what this quasi-charged qubit is, you basically just need to search in this parameter space for what values of inductance, capacitance, and the Josephson energy you need to choose. So for the charged qubit and transmon, you basically need to set inductance to infinity. For phase qubit, it doesn't need to be infinity, but you can kind of tune it. For for Fluxonium, you need this inductance to be kind of large, but and so on. So what about quasi-charge? And so the thing is that for quasi-charge, just like turning charged qubit into a transmon, you need to shunt the junction by a very large capacitance. That the pictures of which you're kind of seeing all over the place. In order to go from a flux qubit or Fluxonium to a Blochnium, you need to shunt the junction by a very large inductance. So large, it has to be larger than the superinductance that we use for Fluxoniums. And so it was kind of interesting to see if you can make it. So what are our limitations for this? Well, when you're making inductors out of Josephson junction chains, if you make the chain too weak, you're going to get phase slips, and that's basically going to ruin the inductive response and make them bad. And the other way to increase the inductance is to make it long, but when it's long, it just becomes a big piece of metal, and it has a self-capacitance, and that will too destroy the inductive response. And so our solution to implementing Blochnium was to basically minimize stray and maximize the inductance per unit length by basically ripping off the Josephson chain from a substrate, because our substrates, they have large dielectric constant. For silicon, it's like over 10. And so that saves you on capacitance. As a result, you can make the chain longer. And so the kind of effective impedance of this inductive element that we could achieve was over 200 kilo ohms. So that's like a challenge to everyone. Try to design something with L omega bigger than that. That would be a fun exercise for pretty much the entire electromagnetism. You can also play some games with it. You can roll the chain like this. It actually works. This trick was invented by my student Ray Mencia. I was very impressed by this, especially by how stable the devices are and that they actually work. But so here comes this dual of transmons. So what you do, you just measure the spectrum of this thing. And what you see here is the dashed line is actually an experiment. And the solid line is a theory where you're basically writing a transmon Hamiltonian where there is this charging term where it's now flux charging. So there's a certain quantum number of phase slips, a discrete number of phase slips. They're offset by an external flux. And then there is this, the dual of the Josephson energy, which is basically a Bloch band of a Josephson junction. Why it's called a Bloch band, it's a long story, but the point is that there's basically, you can think of this device as if a junction behaves as a capacitor whose capacitance is periodic and in charge that travels through it. And then the inductance looks like a mass to this variable, and it's totally dual to what happens in a transmon. And indeed, this picture works. There are some deviations from it at high energies because, in fact, the junction have multiple Bloch bands, and when you go to high energies, you need to take those into account too. So the story becomes a bit more complicated, but in the low energy limit, it's a true dual of a transmon. So the periodic table is established. There are now all 4 fundamental qubit types are available. I know that this periodization is extremely unfair to most other superconducting qubit names because, well, there's no room. But I want to point out that Fluxonium itself does not deserve a name according to this periodization because it's just a flux qubit. Unfortunately, fortunately, history works differently, and some names stick, even though they are not supposed to be there from fundamental considerations. And that's why it's kind of fun to work in this field, because even though your qubits is not supposed to deserve a name, you can still name it and see what happens. I want to point out that this Blochnium thing, where we're basically looking into, okay, what's the highest inductance you can make and see, actually sparked 2 really cool ideas from these groups from Austria, from Vienna and Paris. So in Vienna, these guys basically figured out that you can actually make a really large inductance from just by making a spiral of a regular aluminum wire. And the point is that if you make the spiral in the right way, you really reduce stray capacitance. And I myself wasn't aware of this trick, and I find it very impressive. So they can achieve a remarkably high inductances, maybe not as high as what I showed, but actually almost that. And then the other trick was introduced by the Paris group, by Clark Smith. So they basically said, well, what if you have a junction where kind of charge tunnels in units of 4e, not 2e, then you kind of, if you do the math, you'll see that in order to implement a Blochnium, a quasi-charged regime, you need an inductance which is 2 to the 4 times smaller. I think it's 2 to the 4, but 2 to the 4 is 16. So that's a big win, and they show that indeed you can kind of do it. So. And now I'm going to switch gears and describe sort of the more boring Fluxonium qubit that we designed to have high coherence. So this was sort of work that started around 16, 17, and then It's just this design. So what we have here is there's a squeed loop. The very first qubit had a squeed loop, so we can tune the Josephson energy. This is the chain. We use this kind of 3D transmon style antenna capacitance, although the total capacitance is quite a lot smaller. And we could couple it to a regular rectangular copper box cavity. And so this is the kind of spectrum you get for this qubit when you apply flux. You sort of simultaneously go through the cycles in the big loop and then slower in the small loop. And what happens is that basically when you make the Josephson energy of the squeed large, you get this decoupling of the fluxon transitions, which just kind of go zigzag with flux, and the plasmon ones, which are relatively flux independent. And this way, it all makes sense. But it's not a good qubit because you have either a plasmon, it just looks like a transmon, so you didn't really change anything, but the fluxon is depending, the transition frequency depends on flux, so it's not great either. But if you go to this double sweet spot where the Josephson energy of the squid is minimal, and also you're kind of at the sweet spot of the big loop, you basically get the kind of Fluxonium spectrum that we like. The qubit transition you kind of can't really see on this plot. It's it's kind of below 1 gigahertz, while the next transition is, you see, around 2 to 5 gigahertz, depending on the design. And that's basically it. It's not really different that much conceptually from the original device. But so it works pretty well. And of course, we've measured many qubits, but I'm going to show you only the best one. Just to impress you more. So this is the case for the best that we've seen. So this is the spectrum. So you see here we chose the qubit frequency around 160 megahertz, and then the next transition is around 5 gigahertz. This is a Ramsey fringe. No cheating here. And it corresponds to the T2 star of bigger than a millisecond. And just to kind of point out that this is not just some kind of weird decoupled qubit that has long coherence, but you can't do anything with it. Actually, it's still coupled, so you can do the gates, no problem, and it's stable enough that you can benchmark them to a fidelity of better than 4 nines. And the funny thing is that Aaron Sommerov, the student who did this, it was his first benchmarking thing. And imagine what a student feels when the first gate you benchmark is 4 nines. So I'm pretty sure there are some mistakes in tuning this up, but we decided to stop at 4 nines is good enough. You can get your PhD. So cheers to Aaron for this. On a more serious note, you can immediately see from this qubit that it's actually limited by materials defects. And the way you do this is you just sweep T1 versus flux, which also tunes the frequency. And then you repeat this sweep again in about 24 hours. And you see this kind of rather complicated pattern of kind of T1 going up and down in a reproducible way. And so that data, without any kind of theory, eliminates any kind of out of equilibrium mechanism, because then you would not be able to match it. And it does look like you just have sort of materials defects. Of course, it's not clear from this data from which part of the circuit, but we suspect that it's probably, at least some of it is coming from just the capacitance, because it wasn't really fabricated with any caution at all. It's just some random silicon substrate and just a plain deposition in a basement. But it's nice to see that, you just, if you improve the fab, you can either improve this T1, or at least you will get it along in large arrays of qubits. So the other thing that is quite straightforward to see is that flux noise is indeed irrelevant. So this is an echo time as a function of flux, again, in this best case scenario. And you see there is a sizable sweet spot in which you basically get a T2 above a millisecond, which is basically enough to just kind of say that I don't have flux, I don't need to worry about it, at least if you stick to the sweet spot. So now I want to explain one thing. I mean, I get this question a lot, is that I just showed you for a qubit with a 160 megahertz frequency that is coupled to a cavity that has readout frequency of about 7 gigahertz. How come these two things are even talking to each other? And the answer is that, well, when you calculate dispersive shifts, it's not the qubit transition that determines it. And the way to think about it is that so I have here an example of a 3-level system where the first transition is very low and the next transition is kind of high, and there's a cavity at nu zero somewhere nearby. So what happens is that when you're in the ground state, you're shifting the cavity by a little bit, and this little bit depends on all transitions from ground state up. And whenever some of this transition is nearly resonant with the cavity, there's going to be a big effect. And in case of Fluxonium, there's a selection rule. So you see, when you're in 0, the transition 0-2 is forbidden, while when you're in 1, the closest transition is 1-2, and it's allowed. And as a result, the chi0 and chi1 would take very different values, and that's how you get a dispersive shift, even though the qubit is highly detuned. So with this understanding, you can go further and say, well, in that case, do I even need a cavity to read out this kind of qubit? Because it does remind you of atomic clocks, where you have some kind of hyperfine low-frequency transition and optical high-frequency transition. Of course, here the difference is not that big, but still. And so I asked my guys to think about this, and what they did is said, well, okay, let's just replace the cavity with a coaxial to waveguide adapter. Basically, it looks like a box, but it doesn't resonate. It just couples the chip to a coax cable. And let's look at the fluorescence of the transition 03 in this particular case, because it's an allowed transition. And it's a strongly allowed transition, so you can see its fluorescence. So when you drive it hard, the kind of reflection signal changes, and this data was shown for transmons and flux qubits by Oleg Astafyev and Perdelsing's groups. And so the difference here is that this now, with this multi-level system, this fluorescence should be dependent on whether the qubit is in 0 or not. Because if it's in 0, it fluoresces, but if it's in 1, you're like off resonance, so you should see no signal. And that's indeed works. So we used basically this fluorescent signal to read out the qubit, and we've seen T2 star around 50 microseconds, which is not record-breaking, but you have to remember there's no cavity there. So it's a qubit directly coupled to traveling waves. And so, and yet it can be coherent, and you can still read it out. I don't think this readout can, replace dispersive readout, just because dispersive interaction has many other advantages. But what it shows you is that you can use this qubit in waveguide QED as kind of quantum filter. So you see, depending on the qubit state, is going to filter some high frequency radiation, differently, and that actually can have applications. I'm going to show you one of them sort of towards the end of the talk. And now I'm going to tell you our story of 2-qubit gates. So we decided to try this direction where we designed the minimal possible setup for 2-qubit interaction. So we just literally fabricate 2 qubits next to each other. They have static capacitive coupling and a joint dispersive readout. There's also only one port to drive both qubits. So, and the idea was, okay, so what can you squeeze out of this kind of minimal setup? So the first question is, well, how come these qubits interact, right? Because you would say that you reduce their frequencies, so they live longer, but they're probably also going to interact weaker with each other. And it's true if you only take into account a computational subspace. However, if you go to the non-computational subspace, those states involve higher frequency transitions, and they interact much stronger. And notably here, you kind of can try to excite the 1-2 transition of the red qubit or of the blue qubit, and you will see that it depends on the state of the other qubit, the frequency. And this frequency difference, big delta, can actually be easily around 10-20 megahertz. It's just like if you want to couple 2 transmons, that's what you're going to get. And so then if you try to connect computational and non-computational subspaces, try it as 1-2, drive as 1-2 transition, you're going to induce Rabi oscillations, and you see there have 2 resonances, sort of one when the second qubit is in 0 and the other when the second qubit is in 1. And that's basically a mechanism to accumulate conditional phase shift. So to get it right, you need to match this kind of Nesterov condition. So Kostya Nesterov was the guy who kind of did this calculation for us. And the point is that if you drive somewhere in between these two frequencies, you're going to travel on a Bloch sphere of the 1-2 transition of the first qubit, synchronously with the Bloch sphere of 1-2 transition of the second qubit is in 1. And so you see when they're doing this kind of simultaneous rotations, you're going to come back from the non-computational subspace to the computational subspace with zero leakage. And so if you then optimize the driving amplitude, you will see that you're going to get sort of a CZ gate in about 1/delta time, which in our case is around 50 to 100 nanosecond. So we tried that, well, this is the standard sort of conditional Ramsey fringe, where you see that the fringe shifts by pi depending on the state of the other qubit. And we benchmarked this operation CZ when you apply it multiple times up to n equals to 10 times. And you sort of see that the fidelity drops linearly, which is a good evidence that you don't really have coherent errors. It's just limited by decoherence. And in this particular device, even though I showed you that we have millisecond, qubits, okay, in this particular device, T2 was 10 microseconds because, it was a different person, different fridge, different wiring. And even with this pretty mediocre T2, we could get above, below 1% error, which is actually, I think, the first time kind of a non-transmon system reaches this kind of fidelity, which basically says that there is life beyond transmons. Another good trick that we found, which is again, it's known in transmons, but it's just that it works much easier with fluxoniums, is that you can cancel the static ZZ interaction, which is always there because there's a static capacitive coupling. And the way it works is that the ZZ interaction in case of fluxoniums comes because the higher states push on 1-1 state and on 1-0 state differently, so you get some ZZ. And so to cancel it, you just basically need to undo this push by applying some off-resonant drives, again, connect around 1-2 transition frequency. And that basically works quite well. So in this particular case, you see we're driving around 1-2 of one of the qubits at a Rabi drive of around, you see 30 megahertz. It's not a particularly strong drive, and you basically cancel the conditional Ramsey fringe oscillation. So as if there's no ZZ, at least it's below 20 kilohertz, which was limited by the coherence here. And that's a useful trick because it basically it sort of allows you to undo the static interaction even though you have capacitive wiring, and allows you to avoid more complex circuits. And then there's a second approach, which is even more surprising. It's actually based on cross-resonant interaction that you all know pretty well. I'm not sure what was the first paper on cross-resonant interaction. Maybe it was by Chad and Michelle in 2010. But in any case, I mean, the point was that you have two qubits, but you drive one qubit at a frequency of the other qubit. And the idea is that, well, if you reduce the qubit frequencies, you assume that cross-resonance interaction would slow down. But it's actually not true because, again, of the higher level. And so the way it works here is that I'm driving a qubit B through qubit A, so at the resonance frequency of B, and you see I have a contribution mostly from 0-1 transition, which I can basically cancel with a direct drive, and the qubit B doesn't respond, so it doesn't Rabi oscillate. However, if the qubit A now is in one state, when I apply the same drive, the transition 1-2 kicks in, just like in the dispersive shift calculation. And if 1-2 is not too far from this frequency of the drive, it's going to get a big kind of amplitude through, and you're going to get direct drive on B. And so this way you can actually get a pretty strong cross-resonance interaction, even though at least one qubit frequency is very low. And this experiment was recently accomplished by Cheng Wang's group at the University of Massachusetts Amherst. So this is again the kind of the two Rabi oscillations, conditional Rabi oscillations. So you see it works. And they benchmarked this gate to 995. Again, limited by pretty unimpressive coherence and also some problems in the RF setup. So we're pretty sure that this is a good way to achieve much higher fidelities. So, how much time do I have left? Perfect. So, 5 or 10? Wait a second. You guys have contradicting reports. Okay. Good. Perfect. So here's my summary, and I want to read through it, but like, hold on. So I guess what I wanted to show with my presentation is that basically from what we've learned from this kind of up to 2-qubit Fluxonium experiments is that there's really a pretty good potential to lower gate errors if you just build the same kind of brute force quantum processor but using Fluxoniums. The 3 reasons for this is one is that you significantly reduce coherent errors just thanks to the much stronger harmonicity. That's kind of an obvious one. And indeed, it shows up in the experiments because we kind of achieved all these fidelities that I think was taking quite a lot of time to get the same data with transmodes, and we don't use any of those tricks. We just apply drives, and that's it. There's just no leakage. Another thing is that if you do nothing, you get at least longer qubit storage time because the qubit frequency is lower. It doesn't mean that you need to lower it to 0, but there is some choice of frequencies, and believe me, the qubit at 500 megahertz lives a lot longer than qubit at 5 gigahertz, that I can tell you for sure. And then there's also the parameter space for optimization of Fluxoniums is kind of 3D because you can change both EJ, EC, and EL quite a lot and still get an interesting spectrum, while in transmodes you kind of have to keep EC around like 300 megahertz for the unharmonicity versus charge noise trade-off, and then you kind of want to keep the frequency around 5-ish gigahertz, so you kind of nail to a very narrow space. And the other conclusion from this data is that the Josephson chains are actually quite reliable circuit components if you need to kind of tune up your inductances. They seem to be causing no problems for quite complex experiments. I also left aside questions that I usually get. So one is about readout initialization fidelity. So there's a lot of work on this done, and I just didn't have time to review it, but basically it's all fine. And there have been recently really impressive fast flux tuning experiments. I mean, I talked just about all microwave gates, but you can also tune flux, and apparently it works pretty well, actually better than what I described here. So that's a nice, exciting direction. But in the end, you see, people ask me, so what's, can we, what will Fluxonium add to the quantum computing effort? Will I get like a quantum computer faster? And the answer is that, well, you'll just maybe get a lower gate error, but you're going to still get the same problem of, okay, now you need to build a quantum computer out of this. And this may be depressing to at least some students, right? Because you do all this hard work, but in the end, you're still facing this problem of just having maybe slightly better qubits, but still, doing the useful quantum computing. And so, as an epilogue to my talk, I wanted to ask this question. Well, okay, can I demonstrate to you any kind of useful applications of Fluxoniums? Something that you can do that is interesting, useful, and that you absolutely cannot do with transmodes. And at least I have recently found one example that I myself was quite interested in, so I want to share it with you. And so the idea is very simple. So imagine a photon in a nonlinear medium, and you ask yourself a question, well, what's going to be the fate of this photon? So you know that if you just place photon somewhere, usually its fate is to be absorbed by something and it's going to disappear, right? That's the T1 of the cavity. That's what happens to photons. They usually disappear whenever they encounter matter. But imagine you're placing them in a media which is so nonlinear that something else might happen to them before they get absorbed by matter. And this media was implemented by my group recently. So it's literally just a Fabry-Perot cavity with many modes. And to make it so we make this cavity by making this long Josephson junction chains. And the only thing these junctions do is just they slow down light such that you can fit more modes in a shorter device. And then you just couple fluxonium at one end of it. And that just makes the photons to feel some nonlinearity. And what we found is that this nonlinearity can be so strong that a photon is more likely to decide to split into two before it gets absorbed. And then those two photons are more likely to split into another two before they get absorbed. And as a result, you're facing this kind of an interesting story that you're placing one photon into some high frequency mode K, and then you see that it has quite a large number of 2-photon combinations or 3-photon combinations or 4-photon combinations, all degenerate in energy with the initial state, which makes you wonder, well, does the notion of a photon even make sense if all these manifolds become coupled? So the reason you've probably never seen this picture before is because if you replace fluxonium with a transmon, this coupling is 0. If you do it with a flux qubit, it's actually there, but because flux qubit is so incoherent that you can't resolve it. And so here, this combination of strong nonlinearity and kind of low, high coherence allowed us to see these effects. Oh. Did it? Did it? Yeah. Okay. I think a slide is missing. The final slide is missing somehow. I have no idea. But okay, my time is up, but I have no idea what happened. But I guess I'm going to have to keep it to theory. So in the end, we've kind of succeeded at building a media where photon doesn't exist as a single particle excitation and just kind of keeps evolving into more and more particles. And we're wondering if you can even describe this kind of electromagnetic field with the concept of a photon. So that's sort of the first application to my mind where fluxonium was kind of useful and shows something interesting. Okay, thank you very much for your attention. And so.
Thanks a lot, Vlad, for that really interesting talk and very interesting ending. We have time for questions. Please. Anybody? Right. Okay.
So I know you didn't get to the data for the last slide, but do you see that it oscillates back into the single mode, or does it like thermalize? Because I think some of this is similar to some of the thermalization questions that came up in like Bose-Hubbard physics. Okay, you probably had a slide on that.
Yeah. Well, like I said, I have no idea what happened with the slide, but I'm happy to show it, of course, offline. But so what happens is actually quite interesting because depending on what kind of nonlinearity you engineer there, because you can imagine that depending on the, even the same qubit parameters are different. And so there's a regime where there's many-body localization, meaning that a one photon evolves into 2 to 3, and then kind of gets stuck. So you kind of basically form a many-body Fock state, which involves quite a lot of photons, but still it's restricted to just maybe few components. And that happens because there is some disorder in the system and dispersion. However, if you tune up interactions and make them stronger, it looks that it actually can delocalize, and then what you see is that your photon has a lifetime, but not because it's getting absorbed, but because it sort of decays. And so this kind of crossover between localized and delocalized regime is what I find sort of like one of the most interesting topics that you can pursue with this system, because it's very simple. It doesn't require Pedram's 70-something qubit quantum computer, but you can address some of these questions by just simple spectroscopy experiments. Thank you.
Any more questions? Over there on the left. Over there, in the front, yeah.
Can you comment on the thermalization of your low-frequency qubit? Because it's such low frequency, it must be thermally excited at 10 millikelvin.
It is.
So do you have a problem then with initialization or not really?
No, not really. Like I said, this question comes up all the time, but we find it sort of the least interesting one because actually initialization of qubits was done long time ago. If I remember correctly, Will was one of the people who was initializing flux qubits, which also were, designed to have low frequencies. I mean, there were some flux qubits very low frequencies, and they did the kind of laser cooling type experiments where you connect it to some lossy transition, and you remove entropy from the system. So there is actually a myriad of tricks to do this, and the entire atomic physics is based on this because atomic clocks, they have 10 gigahertz frequency, but they operate at room temperature. So they figured it out somehow, right? And so do we, mostly using their tricks.
Thanks.
Okay, this question at the back.
It's a very nice talk. A question on the 2-qubit gates. So am I correct in saying that the second excited state actually gets populated during the 2-qubit gate?
Right. So depends on the approach. So in the first approach, you do get you get sort of a significant occupation of the second excited state, but for a short amount of time, and then you go back. So you actually cycle through the second excited state. And of course, anticipating your question, to get the gate error low, you want to have not only your qubit to live long, but also your second excited state to live long too. And depending on the speed versus the coherence time, that's what's going to determine the fidelity. In the second approach, that's not the case. In the second approach, the second excited state is driven highly off-resonantly, and its coherence is basically has negligible effect on the gate performance, which is why probably cross-resonant interaction has a higher chance of kind of be working in a large-scale system. However, this ZZ cancellation, which is important for the cross-resonance gate, because if you don't cancel ZZ, cross-resonance gate is not that useful. You kind of go in between. You populate the 2-state, but just a little bit, and that because all you need is just to cancel the static ZZ shift. You don't want to induce a big one, and this way you're still sensitive to T1 of the 2-state, but not that much. And so it's really the combination of ZZ and CR that I think will give you the sort of the more likely way to proceed with larger systems.
Okay, maybe one last question or comment. Yeah, over there, the front.
Hi, very nice talk. Maybe more amateur questions like, can you comment about operating the qubit at a frequency much lower than 500 megahertz? You mentioned that it's probably not so great to operate it at a much lower frequency. Can you comment about that? Like, why is it not good to operate it at a much lower frequency? Is it too slow or coherence and something?
So I guess you're asking why low frequency helps.
Why don't you want to operate it at a much lower frequency?
Oh, at much, okay. So
yeah, sorry.
Well, so you see, when you consider, just from the viewpoint of energy relaxation, if you consider some atom decaying due to coupling to some baths, usually the density of states for any kind of reasonable mechanism, it goes up at higher energies. So meaning that it's usually much easier to emit a high energy photon than a low energy photon. However, as you go down in frequency far below the temperature, you get this Einstein factor of kBT over omega, which enhances your relaxation rate. And now you see going too low might not actually help you. At least you get like a wrong factor against you because of this kBT over h bar omega. The other problem is that, well, you see when you have one qubit at 500 megahertz, the other 600 megahertz, you get quite a lot of space to assign your frequencies. If they're all at like 20 megahertz, 21 megahertz, 22 megahertz, it becomes crowded. So I anticipate some purely engineering issues with that. And my point is that 5 gigahertz just seems too high. 500 seems a lot better, but I'm not sure if 50 is better than 500. It might be, but I don't have evidence of that. Yeah, it's I'm like I said, I'm not sure it's optimal because in fact you can have one qubit at 1 gigahertz and the other at 100 megahertz and still make a terrific gate. But just from the view, yeah, we haven't explored much below 100 megahertz. My colleague Dave Schuster is, I think, a big fan of much lower frequency qubits. So I think he made one at around 10 megahertz. So we'll see how that will work, with the 2 qubits. And I think it can. It's just like you'll probably find out soon.
Okay, let's thank Vlad again for this fantastic talk. Okay, we now continue with the session on unconventional qubits. Some interesting names coming up. Since I forgot to introduce myself, I'm Rajamani Vijayaraghavan, or more simply known as Vijay. I am a professor at the Tata Institute of Fundamental Research in Mumbai. The first talk in this session is going to be given by Eric Kuper from IQM Quantum Computers, and he's going to be telling us about the Unimon. Eric.
Okay, so hello everyone. It's my pleasure to be here and thanks for the introduction. So my name is Erik Hyppä. I'm a quantum engineer at IQM and a PhD student at Aalto University. Today I'm going to present one of our research projects at IQM. Namely, I'm going to tell you about the Unimon qubit, that is a novel island-free superconducting qubit that we have developed at IQM in collaboration with QCD Labs at Aalto University. I will begin my talk with a brief introduction and explain why we think that it's interesting and important to study novel superconducting qubit circuits. Then I will introduce you to the Unimon and its theory. I will also share some experimental results that we have obtained with the very first Unimon qubit samples that we have fabricated at IQM. And finally, I will summarize my talk and also point out some key challenges for the future. So, as you all probably know, there has been tremendous progress in the development of superconducting qubits during the past 2 decades. But nevertheless, the errors in the single and 2 qubit gates are still greatly limiting the computational power of current superconducting quantum computers. And these gate errors can be caused by multiple sources. So you can have leakage to non-computational states, you can have decoherence, you can have coherent calibration errors, or you can have different types of crosstalk or even some residual interactions. And there exists multiple solutions that you could try in order to further reduce the gate errors. Some of these solutions are, for example, that you could try to develop novel pulse shapes for your gates, or you could try to develop novel types of couplers to implement new gate schemes. But one interesting solution would be to develop new type of qubits that would be robust against some of the previously mentioned error sources. And this is the focus of my talk today. And now I will introduce you to the Unimon. And first, here on this slide, I am listing some key properties of the qubit. And on the following slides, I try to explain the theoretical background behind these properties. So first of all, the Unimon has a high unharmonicity as compared with transmon qubits. The Unimon is also fully protected against low-frequency charge noise, and it also has a reduced sensitivity against magnetic flux noise. The Unimon is also based on a very simple structure, since it incorporates only a single Josephson junction that is placed in a gradiometric resonator. Finally, we only use geometric inductors in our circuit, so we do not need superinductors in our circuit. And here on this slide, I'm showing you a map of some of the most common superconducting qubits. And to understand this map, I'm showing you the same circuit diagram that Vladimir was showing you in his presentation. So we have this capacitance and inductance as a Josephson junction in parallel, and this circuit can be used to model or approximate many of the existing superconducting qubits, and it can also be used to approximate the unimon around its optimal operating point. And as Vladimir explained, even though we have the same circuit diagram, we can have very different physics depending on the energy scales of the capacitor, the inductor, and the Josephson junction. And this is illustrated in this map below. So here on the y-axis, we have the Josephson energy divided by the capacitive energy, and on the x-axis, we have the inductive energy divided by the capacitive energy. And for example, transons are located on the y-axis in this figure because they do not have this inductance. The Fluxoniums have a quite small inductive energy because they incorporate this large superinductor that makes them have a high coherence. But the unimon is located in a new parameter regime where we actually use a quite high inductive energy because we only use these geometric inductors, and even more importantly, we have designed the circuits so that the Josephson energy and the inductive energy are of almost equal magnitude, which enables us to have a high anharmonicity even though we do not have any superinductors and even though we have a quite high capacitive energy in our circuit. Well, how did we then implement the unimon in practice? So the unimon is based on a grounded coplanar waveguide resonator that incorporates a single Josephson junction at the middle of the center conductor. And here I'm showing you a schematic of the circuit, and you can now probably visualize in your head that similarly to an ordinary λ/2 resonator, this circuit can support multiple normal modes. And the key thing here is that the Josephson junction is a nonlinear circuit element, and it converts some of these normal modes into anharmonic oscillators, and then you can choose one of them as your qubit. And so far we have chosen to use the anharmonic mode with the lowest frequency as our qubit because it turns out to have the highest anharmonicity. Now I will briefly explain how we can theoretically model this circuit, and it is actually not so simple because it is distributed in its nature. So we need to start from the distributed element circuit model that I'm showing at the bottom of the slide, and then we take the following steps. First, we solve the classical normal modes of the circuit by approximating the phase biased Josephson junction as a linear inductor. Then we make a single mode approximation, and we only take into account the mode that we want to use as a qubit. And finally, we quantize the obtained classical Hamiltonian by imposing the canonical commutation relation between the charge and the phase variables. And here on the slide, I'm also showing you the final result for the Hamiltonian, and it is rather similar to the Hamiltonian of Fluxonium qubit, but there are also some differences. For example, the capacitive energy and the inductive energy are no functions of the applied magnetic field in the case of the unimon. Now I want to explain why the unimon is protected against low-frequency charge noise, and this comes from and this has the same origin as in the case of Fluxonium qubits. So we have a Josephson junction that is inductively shunted, and as a result of this, the potential energy of the unimon is a non-periodic function in terms of the superconducting phase variable, and the Hamiltonian then becomes independent of any DC offset charge. And this is what gives us the protection against low-frequency charge noise. And here it's good to note that we use a geometric inductance instead of a junction array, so we should have full protection against low-frequency charge noise, and also it should be possible to fabricate the parameters of the inductance in a very reproducible manner. And on the other hand, the protection against flux noise arises from two factors. So first of all, you can see that the circuit of the unimon contains two loops, and actually the frequency of the qubit is dependent on the difference of the magnetic fluxes applied through the two loops. So this gives us some protection against magnetic flux noise. The other thing is that similarly to some existing superconducting qubits, we have a flux-insensitive sweet spot that is the optimal operating point of the qubit. And at this sweet spot, the frequency of the qubit is insensitive to changes in the applied flux to the first order. As the final theory remark, I want to try to provide you some intuition how come we can have this high anharmonicity even though we do not have any superinductors in our circuit and even though we have a quite large capacitance in our circuit. And this comes down to the fact that we operate the unimon at the half-flux quantum point, where we can write the Hamiltonian, as I'm showing you on the slide. And now to understand where this high anharmonicity originates, it pays to make a fourth order approximation. And here you can now see that we have quadratic potential energy terms that come from the inductance and that comes from the Josephson junction. And in the Unimon, we have designed the circuit so that the Josephson energy is almost as large as the inductive energy. And as a result of this, these quadratic potential energy terms are almost fully cancelled, and the higher order potential energy terms dominate in the Hamiltonian. And then you can think that the potential energy becomes more anharmonic, and you also have this enhanced anharmonicity. And here at the bottom of the slide, I'm showing you a theoretical prediction for the anharmonicity of the Unimon as a function of the applied external flux difference. And you can clearly see that the anharmonicity is indeed greatly enhanced at the half-flux quantum point. And for these particular parameter values, the anharmonicity is about plus 500 megahertz at the half-flux quantum point. And here it's good to note that this is not the first qubit that uses this kind of cancellation of the quadratic potential energy terms to enhance the anharmonicity. And in the quadrant qubit that was introduced by Will Oliver's group a few years back, there is a similar kind of phenomenon, but the difference here is that we use a geometric inductance instead of a short junction array. So we should have this full protection against low-frequency charge noise. Let me then move on to describe some experimental results. And so to study the Unimons experimentally, we fabricated some prototype chips, and each of these chips contained 3 Unimons. And on these chips, each of the Unimons was capacitively coupled to a readout resonator, so we could use ordinary dispersive readout to measure the state of the qubits. Each of the Unimons was also capacitively coupled to a microwave driveline so that we could perform single qubit gates. And the flux difference through the loops of the Unimons was controlled with an external coil. And here I would like to point out that the Unimons were designed so that the characteristic impedance in the circuits was about 100 ohms, so we didn't really need any superinductors. So first, I'm showing you some results for a resonator spectroscopy experiment and for a qubit spectroscopy experiment for one of the qubits that we characterized. In the resonator spectroscopy experiment, you can see that there is nothing special. We have these avoided crossings when the frequency of the qubit crosses the frequency of the resonator. The data for the qubit spectroscopy is perhaps more interesting. And here, from this data, first of all, we can measure the frequency and anharmonicity of the qubit at the sweet spots. And at this half-flux quantum sweet spot, we measure a frequency of about 4.5 gigahertz, and the anharmonicity was about 430 megahertz, which is significantly higher than in typical transmon qubits. At the other sweet spot, the anharmonicity is much lower. And in this figure of the qubit spectroscopy, I'm also showing you a theoretical fit of the model that I briefly described to you earlier. And what is good to note here is that around the sweet spots, the fit is very good, and it's also good between the sweet spots. And what is even more important is that when we compare the fitted circuit parameter values to the designed values in the table that I'm showing on the slide, you can see that the values agree very well. And this means that our theoretical model is working well to describe the physics of the circuit. On this slide, I'm showing you the measured sweet spot anharmonicities as a function of the Josephson energy for 5 Unimon qubits. And we can make a few interesting observations from this figure. So first of all, we see that the measured anharmonicity does indeed increase drastically when the Josephson energy approaches the inductive energy of the circuit, and the second order potential energy terms are cancelled more and more perfectly. Then we can also see that the measured anharmonicities agree well with the theoretical model that I'm showing you with the solid red line. And finally, we can see that the anharmonicities for qubits A, B, and C are much higher than for typical transmon qubits. Then here is some data for the T1 for one of the qubits. So at the half-flux quantum sweet spot, we measured a T1 of about 8.5 microseconds. So I would say that this is decent, considering that these were the first ever samples that we fabricated. But of course, it is lower than for the state-of-the-art transmons and Fluxonia. So we wanted to figure out what was the limiting source of relaxation error. And to do this, we also measured the T1 as a function of the qubit frequency. And then we compared the experimental data against different, some predictions based on different loss mechanisms. And what we found out was that dielectric losses are the most likely culprit to limit the relaxation time. And we estimated that the quality factor related to these dielectric losses was about 350,000. We also wanted to characterize the coherence of our qubits, and so we measured the Ramsey and echo T2 times, and for the same qubit, they were about 3.1 microsecond for the Ramsey T2 and about 9 microseconds for the echo T2. And we also want to measure the flux noise density, and to do this, we measured the echo T2 time as a function of the applied flux difference, and we extracted a value of about 50 microflux quanta. And to give some perspective for this value, this is about an order of magnitude higher than for state-of-the-art squid loops. And then we, of course, wanted to show that because we now have this qubit that has a quite high anharmonicity and reasonable relaxation and coherence times, so we can use it to implement fast and high-fidelity single qubit gates. And here, you can see some data where we have measured the gate fidelity as a function of the gate duration. And you can see that the measured fidelities were practically coherence limited down to the shortest gate duration of 13 nanoseconds. And for these 13 nanosecond gates, we measured a gate fidelity of about 99.9%. We also monitored the stability of our gates by performing repeated randomized benchmarking experiments over some longer periods of time. And we saw that, for example, in this 8-hour time trace, the gate fidelity stayed practically constant. As the final experimental result, I'm showing you some single-shot readout data. And here I would like to emphasize that we did not have any parametric amplifiers in our amplification chain. We only had a cryo-HEMT. But despite of this fact, we managed to reach a quite good readout fidelity of about 89%. But we needed to use quite a long readout pulse because these first devices were not optimized for very fast readout. So now I will summarize my talk. So I have introduced you to the Unimon. That is a new superconducting qubit with some quite nice properties. So the Unimon has a high anharmonicity as compared with transmon qubits. It is immune to low-frequency charge noise thanks to an inductive shunt. It also has a reduced sensitivity to flux noise thanks to gradiometricity and a sweet spot. And finally, it has a very simple structure since it incorporates only a single Josephson junction and we do not need any superinductors. To list some key challenges for the future, I would like to say that first of all, we would still want to reduce the sensitivity of the qubit to flux noise even further, and we already have some ideas how we could improve the design and fabrication to enable a higher T1. And of course, eventually it would be nice to demonstrate that we can implement a high fidelity 2-qubit gate. But all in all, we expect that improvements to design, fabrication, and materials will further improve the properties of the Unimon, and it will be a good candidate for implementing quantum gates with very high fidelities in the future. With this, I would like to finish my talk, and here I have put some details for our archive preprint, so please check it out if you found this talk interesting. And I would also like to thank all my amazing co-authors for their efforts. So this has been a joint effort from many people. And now I would also like to thank you for your attention. And if you have any questions, I'm happy to answer them. Thank you.
Thank you, Eric. We have some time for questions. Over there on the left.
Great, very nice talk. So you showed your fidelity versus time, and you went down to, let's say, 13 nanoseconds. What was the reason for not going shorter? It has sort of a nice slope.
So the reason why we didn't go shorter was that actually our AVGs couldn't do shorter pulses. So this was like the limit of our electronics.
Thanks.
Okay, there was another question over there. Yeah.
So you mentioned that the characteristic impedance of your transmission lines that's attached to the Unimon, that's 100 ohms. can you keep increasing that and maybe kind of approach the regime of geometric fluxonium without having to worry about the parasitic capacitance?
I suppose that you can for sure you can change the characteristic impedance. What you need to consider is that if you want to keep this coplanar waveguide structure, then you need to make the superconducting loops larger, and this might make the qubit more sensitive to flux noise. But we are planning to try different characteristic impedances in the future.
Right, thank you.
Nice work. I was quite curious about your remark that the charging energy of your qubit effectively depends on flux. Can you say a little bit more about this? Because I find it quite unusual and maybe even hard to believe.
Okay, so this comes from the fact that in our model, you see here these voltage envelopes for the qubit mode at 2 different flux values, and these voltage envelopes depend on the applied flux, and this actually determines the charging energy. So this is the reason why the charging energy changes as a function of flux. So, and I don't know if it's like an actual charging energy or if it's just an effective charging energy that we used in a Hamiltonian, but the value that is in front of the charge operator squared is changing as a function of applied flux, at least.
Okay, so I think we have to move on. As time is over, so let's thank Eric again for a wonderful talk. The next speaker is Dennis Rieger from Karlsruhe Institute of Technology, and is going to be talking about the Gralmonium, granular aluminum nano-junction fluxonium qubit. Over to you, Dennis.
Hello, everyone. My name is Dennis Rieger, and I'm a PhD student at Karlsruhe Institute of Technology under shared supervision by Wolfgang Ransdorfer and Johann Popp. I'm very excited to share with you today our recent results on a fluxonium qubit, which we implemented in a single layer of granular aluminum, or short, Gral, which is why we nicknamed the device Gralmonium. In the title image, you can see a false-colored SEM image of the device. And I hope at this point the talk starts to look and sound like a perfect fit for an unconventional qubit session. Now, my job today is to convince all of you that the Gralmonium actually implements an absolutely standard fluxonium all the way until it's not. So stay tuned during the talk to find out where the story deviates from expectations. Let me start by motivating why you would be interested in such a single-layer approach for a qubit. And the reason is that if we can even implement a tunnel junction of a fluxonium in a single layer, then there's many, many opportunities for interesting science to do with these kinds of circuits. So given the fact that granular aluminum has a critical magnetic field of a few Tesla, that makes the platform very attractive for hybrid architectures involving strong magnetic fields. Moreover, since the junction in a single layer does not come with the parallel plate capacitance associated with standard SIS tunnel junctions, you get a low capacitance, high charging energy, and therefore can use it to promote quantum fluctuations of the phase across the junction, which is interesting for novel types of circuits like the 0-pi qubit. And finally, you can really get creative with how you do fabrication. Imagine putting a single layer of granular aluminum, and then simply by tailoring the geometry of the wires, you implement your circuit with different parts having different roles and contributing in different ways to your total circuit. And since that's exactly what we do in the Gralmonium device, I will elaborate on that on the next slide, because you can see the Gralmonium circuit as a way to test the limits of how we can implement circuits elements with granular aluminum. So if you would zoom into a patch of granular aluminum, The material consists of crystalline aluminum grains embedded in an amorphous aluminum oxide matrix. And it's this microstructure which makes the material a high kinetic inductance superconductor, the properties of which we can tune, for example, with the evaporation parameters like the rate of the aluminum or the oxygen flow during evaporation. And on this slide, I actually want to focus on the relationship between the unharmonicity, the nonlinearity of a Graal element, and the volume of that element. So the smaller the volume of the element taking part in the oscillation, the less junctions of this effective chosen junction network contribute, and the more nonlinearity you get for this element. And I will use this dependency on a scale on this slide and put the many types of elements that we can implement with this material. The simplest object that you can think of is a resonator with dimensions in the micrometer to millimeter range, and you will have a nonlinearity much smaller than the line width of that object, which is exactly what you want for a resonator. In a similar fashion, you can implement superinductors for fluxoniums, which we did, and you also want them as linear as possible. Now, you could think of balancing actually the nonlinearity with the line width of an object and get parametric amplification. And this is an active work in progress in the group currently. Now, we've already shown that by using a Graal volume of about 100 nanometer cubed, we can actually implement a Graal transmon where the nonlinearity exceeds the line width of this object. And now the Graalmonium, and in particular the junction of the Graalmonium, is an approach to address the question, can we make that Graal element so small that we effectively get the replacement of a single tunnel junction with a Graal element? Now, the beauty of the Graalmonium circuit is that it actually covers the full scale shown here on the slide. So let's start assembling the circuit, and we start by addressing the most simple element, which is the readout resonator. And indeed, it is implemented as a simple strip line of Graal with a resonant frequency in the gigahertz range. And at the center of this antenna, we couple the qubit to the resonator by sharing a part of the inductance. So here you can see the superinductor loop in a meandered wire, and how the Graalmonium qubit is attached to the resonator antenna. Now, the junction actually closes the loop right here. And if we zoom into that, you can see that it's implemented by confining the Graal wire locally to about 20 nanometer in width. And you can already see that we designed on purpose geometric capacitance in parallel to this junction because of the low capacitance that we get intrinsically, which I mentioned in the motivation slide. And now at this point I will make a claim, and the claim is that we can model the structure that you see here in the most zoom-in SEM of the junction as this effective circuit diagram. So what we call here the nano junction, let's claim that it implements this circuit diagram with the nano junction serving as a single effective tunnel junction in red, which will be the tunnel junction of the fluxonium, and the much wider wire of the superinductor is much more linear, orders of magnitude more linear, and can serve as the superinductance. But at this point, I really emphasize that I made a claim. So let's test this experimentally. And fortunately, the fluxonium Hamiltonian is a perfect test bed for accessing the energy phase relation of the junction. So let me false color code the SEM, like on the title page, and write the corresponding terms of the Hamiltonian. We have in green the inductive energy corresponding to the superinductor wire. We have the charging energy in blue, which corresponds to the total charging energy, including the parallel shunt that we put on purpose. And in red, that's the term of interest, the junction. And we claim that it's the standard cosine phi energy phase relation that we would expect for an SIS tunnel junction. And now the question if that SEM picture really implements, that the structure shown in the SEM picture really implements that cosine phi, that boils down to answering if the nano junction implemented a standard tunnel junction. So let's do spectroscopy on this device and check that claim. And the first thing you want to see is that you actually have a functional qubit attached to your resonator, which you check by seeing avoided level crossings, and we do. And if I would show an extended flux range, they repeat periodically, which is exactly what you expect. And here is the spectrum of the qubit, where in red I show the GE transition, and in blue the GF second transition. You can see that it's looking pretty conventional for a Fluxonium spectrum, and the black line shows a fit to this data by diagonalizing the Hamiltonian shown on the previous slide, and it matches data excellently. From the fit, we get also very conventional Fluxonium parameters, which is about 300 nanohenry of superinductance. The junction Josephson energy is about 20 gigahertz, and the total capacitance is 1.3 femtofarad, where we actually expect about 1 femtofarad from the geometric finger capacitance that we put on purpose. Now, on a gigahertz scale, probably everyone would agree that the fit matches very well. So let's really make that proper and analyze it more carefully, and also test different current phase relations to see if there's any deviation that we can find. So here I show in green the standard sine phi current phase relation, in orange a slightly slanted version, and in red the approximation of a sawtooth-like current phase relation with about 10 terms of higher order cosines. The corresponding energy phase relations look like this. So the standard one is the cosine phi, and the slanted and sawtooth one are sharper in the middle, more pointed. And now here's the plot that you want to see. We fit the Hamiltonian, including these energy phase relations, to the data, and subtract the data, so we get the deviation, and that's what we get. So the standard cosine phi model actually matches the data without systematic deviation, and actually within the statistical deviations of about 2 megahertz here, which is the spread of the points. In contrast, even the slanted version, the orange one, already deviates systematically and by 1 order of magnitude from the data. So after convincing you that the Gramonium indeed does implement a standard Fluxonium spectrum, let's see if it's also a useful qubit. So let's test the coherence. And here you see on the left-hand side T1 energy relaxation experiment, where you get about 10 microseconds of a single exponential decay. And the insert shows some statistics of that value. On the right-hand side, you see a T2 echo experiment, where again we get about 10 microseconds in coherence with a single echo pulse for refocusing. And now you might wonder why I didn't show a T2 Ramsey experiment, which in a way would be the more fundamental experiment to do. And the reason is that that one has a bit of more features. So here's a typical Ramsey fringes plot. And you can see that we get a T2 Ramsey of a few microseconds, but clearly the Ramsey fringes are modulated by a beating on top, which you wouldn't expect. Although actually seeing a beating in a Ramsey, it's not too uncommon, right? We see this in many transmon samples, in some Fluxoniums. So at this point, you wouldn't be too worried. However, for the Gramonium, we observe that this story continues on all time scales. So as an example, here's a Ramsey experiment with the same settings, but measured a few minutes later. And you can see that while the beating is still there, the average qubit frequency did shift by about 1.5 megahertz. So you both have the qubit toggling between two frequencies which give the beating, and now the average qubit frequency of both of these frequencies actually jumped. And as I said, the story continues. So in the following plot, I summarize the displacement in qubit frequency at half-flux on even longer timescales. And the red points are the ones captured by the Ramsey experiments on the previous slide. However, on a daily time scale, we see even larger fluctuations of about 10 megahertz or even 100. And then the most drastic changes are between cooldowns, where we can even get a gigahertz change at half-flux frequency. Now, I want to emphasize that what we observe here does not show a clear trend. So the qubit frequency is not saturating somewhere, like an aging process. It can go up and down again, especially in different cooldowns. And also, it's not a fixed frequency effect. So we do not see these changes only at half flux, which, for example, could be a fixed frequency fluctuator coupled to the qubit. We see that fluctuation across the entire spectrum versus flux. So it rather corresponds to a different set of parameters describing the qubit, and in particular the junction. Then again, this might not be too surprising, given the fact that the granulomium is sensitive to a 20 nanometer cubed volume of granular aluminum. And with that, I would like to conclude my talk. Today, I've shown you that we implemented a single-layer coherent Fluxonium qubit with granular aluminum and a nano junction replacing the conventional SIS tunnel junction. Of course, one of our next steps is to try and stabilize the parameters which lead to the frequency fluctuations of the qubit, and to deliver on the promise that this circuit should survive in magnetic fields, and we want to measure the coherence in strong fields. And if you're interested in that, I recommend that you visit the poster session tomorrow of my colleague Simon Günzler, where we'll show more about that. Thank you for your attention.
Thank you, Dennis. We have time for questions. So on the back.
Thank you very much for the talk. What's the typical yield for this granular aluminium qubit that you guys have? So 20 nanometers, is it hit and miss? Or?
Can you repeat the first part of the question, please?
The typical yield for these structures, where you're trying to get this 20 nanometer granular aluminium.
Yes. So I would say that about 1 out of 4 identically fabricated junctions come out similar to this one, and we can measure a spectrum of the qubit.
Okay, this one here.
Yeah, thanks for the presentation. So you showed this cool-down to cool-down variations, and then if it passed by a little bit quickly, but it seemed that the biggest point was like, I don't know, 6 gigahertz, right? Which is more than your qubit frequency. So you really have like a doubling of the qubit frequency from cool-down to cool-down?
Yes, so that is correct. The most drastic point that you mentioned, it was a change where the spectrum went from the one that I've shown, basically all the way up there to 10-ish gigahertz and very flat in the modulation versus flux. And then the next cooldown, it went back down to a similar version that you saw today.
Okay, great, thanks.
Okay.
So I wanted to propose another sales point for this qubit, which I think is better than magnetic field, is that it seems that you've implemented a junction with a very high plasma frequency, which I think might be difficult with conventional technology and can actually have some applications.
Yep, I agree.
I also wanted to propose that maybe what causes the beatings in these devices in an experiment maybe done by Vijay, or maybe not. So you have this junction, right? So it has channels. I don't know how many channels you probably thought about this. So what if one of these channels is getting occupied by a quasi-particle back and forth? That wouldn't do much to T1, but it can cause some fluctuations of the qubit frequency. So maybe you can look into that. But nice work, thank you.
Thank you very much. I definitely agree, and this is one possible source of origin for these fluctuations. Thank you.
Yeah, maybe just to comment on that, I think the experiment was done by Eli. And I mean, I was with him at some point of time. This was related to the channels in a nanobridge Josephson junction, and they showed that this quasi-particle hopping on and off just causes too much decoherence. So it's interesting, but we'll get back. Another question over there?
So this fluctuation, do you see this in other devices that you make with granular aluminum?
Yes, so that is the case. It seems to be a consistent story at this point. For example, we did see it in the transmon qubit, which I mentioned on one of the introductory slides. Not as strongly because the circuit itself is more sensitive here to the tiny junction. But we do see it consistently across devices, across wafers, and yeah.
So you only see it in the narrow junctions, but not in the like a superinductor type structure.
Probably that's true, yes. And the effect is that in a larger structure, for example, also in a resonator, you just average much more over individual junctions in the junction network, and that makes you insensitive to the effect of individual ones. While here you're really, in a way, as sensitive as you can get to a very small amount of Graal and the junction network.
Thank you.
Yeah. Any other questions? Maybe I can ask a question. It's sort of connected to two of the points made. So you went out of the way to demonstrate that the current phase relationship was indeed sinusoidal, saying that it's an SIS type of junction. I'm guessing that you are suspecting that maybe you're accidentally making nano-bridge Josephson junctions. But wouldn't the EJ value automatically tell you, because it's very difficult to get small EJ in those nano-bridge junctions. So if you're in the right regime, it has to be a tunnel junction. And then that connects with this fluctuations of things of how many channels is this Josephson junction, because the sinusoidal CPR comes from the model where you have many, many weakly conducting channels. So maybe if you can comment on that.
Yes, I do agree with all the points. The EJ, I would say we basically extrapolated from the transmon device, which still has like orders of magnitude more volume of Graal. So it was a bit of a stretch. And we were happy to see that actually the 20 gigahertz that we got was quite close to the expectation. So simply the EJ, it's an indication, I would say. But personally, I feel like the testing the phase relation with the spectrum is very strong, and seeing it basically within the noise of the points was super convincing for us. Regarding the number of channels, in a way, if I understood correctly, you're saying that since it's still a cosine in the end, doesn't that actually tell us that it's similar to a standard junction, a lot of channels with low transparency? So
it should be.
I personally feel like that is still the case. So we're not in the regime of seeing individual channels and like Andreas kind of physics, okay. But to be checked.
Okay, I'm getting time is over. Vlad, you have a quick comment?
Yeah, I just yesterday there was this discussion about whether it's very, very much related to your last comment of whether in this nanowire with a constriction you're making a real Josephson junction or you're getting a quantum facelip like Oleg Astafyev was explaining. So his point was that it's not a Josephson junction. It looks like you're saying, well, in your case, it is really as Josephson as it gets.
Absolutely.
Can you say something about it? I'm just curious.
I mean, I think you just had the perfect summary of what the intentions are. We try to convince you that this is just a Josephson junction, but implemented with granular aluminum.
Okay, let's thank Dennis again for this nice and interesting talk. That's the end of the session on unconventional qubits. I hand it over to Mikko to chair the next session on IQM computers.
Yes, thank you. And right, we have had great talks today, and I've been very happy about the program and how interactive this conference is, and that's wonderful. We still have the last session of today, IQM session, and as I said, we had many nice contributions from very many organizations, and IQMers also put on nice contributions, and we could have just put them to the other sessions, but we actually made a little bit more room to the talks, and we pushed them here because I think they go well together, and maybe people are interested on what IQM is doing on these fronts. I'm going to start with a little bit of introduction. I'm not going to talk very long about IQM itself because many of you already know much about it, but I just want to mention a few things. First of all, IQM's mission is to build world-leading quantum computers for the well-being of humankind now and in the future. So we are really like on this, trying to make the dream come true of the useful quantum computers in the end. And we started about 3 years ago. We really, started the operations when we raised our seed funding round. We span out from Aalto University and VTT, especially from the quantum computing and devices labs, where almost the first 20 members of the IQM team were coming from. But however, now we have offices in 3 different countries in Europe. So we have office in Munich, Paris, and Madrid, in addition to Espoo. And we have almost 200 people working now in the company. So it's been quite of a ride in 3 years to go from 1 to 200. And we are happy to support this conference because we're not only there to make and sell quantum computers, but we also want to expand the scientific knowledge in this community, because we, of course, think, like you, many of you others, that it's like building useful quantum computers is such a big topic, has so many scientific questions to be answered, that we don't think that we can do it alone. We need you and we need the community to make this dream come true. All right. That's what I wanted to say. And then I'm happy to actually let the scientific talks to start on the session. So Julia, please come on stage to talk about creation of maximally entangled states with co-design quantum computing. Julia, please.
Thank you. Okay, hello everyone. I'm Julia and I'm a quantum engineer at IQM, and I'm located in the Munich team, so I'm working in the quantum innovation department in the co-design implementation team. So we are trying to implement co-design algorithms. And today I will present how we prepare a maximally entangled state with digital analog quantum computing. And this we do as an example to explore and investigate the so-called DAQ paradigm. So first, let me start with a short motivation. What actually is digital analog quantum computing and why is it interesting? Most of today's quantum computing platforms either use digital or analog quantum computing. In the digital case, there is a fixed set of single qubit and 2 qubit gates, which makes quantum computation universal. So this is nice. But if the problem is not natural to the device, we have a large overhead in operations. And in the current NISQ era, the noise limits the number of operations. On the other side, analog quantum computation is meant to directly simulate the dynamics of a system with a given Hamiltonian. So this makes it easy to scale up the device, but the problem is that this is not universal. So we can only, of course, do computations where we have the system with a given Hamiltonian. And another fact is that we need to calibrate the Hamiltonian very accurately. Now, coming to the topic of my talk, combining the benefits of digital and analog quantum computation leads us to the so-called DAQ paradigm. And here, analog blocks are combined with single qubit gates. So we re-obtain universality, and we are able to generate entanglement faster. So this is potentially relevant for the current NISQ era. Okay, so let me give an example. As an example, I have chosen the GHZ state, which you can see there in the definition. It is a superposition of the qubits being in the ground and in the excited states. This state is only defined for more than 2 qubits. For 2 qubits, this is just a Bell state. And in the following, I will compare the digital implementation towards the digital analog implementation. So first, let me introduce our chip design, which you can see on the top. For these algorithms, we need a so-called star topology. So you see we have 5 qubits, and all 4 qubits on the side are coupled to a central qubit via tunable couplers. So we need this topology to have the following algorithm. In the digital case, you can see, as I mentioned, we have 2 qubit gates, which are ZZ gates, and we have single qubit gates. When we do the algorithm, we can see that the number of 2 qubit gates we have is proportional to the number of pairs of qubits. When we then go to the digital analog case, we only have single qubit gates and an analog evolution. So this is an analog block, the green thing, where the system evolves naturally. And here, it doesn't matter how many qubits you have, we always have the same depth, so it's constant size. Okay, so far so good. Let's go a little bit deeper into the pulse level scheme, which you can see here. Now you have the pulses, the single qubit gates, and the 2 qubit gates consisting of a flux pulse and virtual Z rotations. In the digital case, you can see we again have the depth, which is proportional to the number of qubit pairs. And in the digital analog case, we have a flux pulse on all the couplers simultaneously with virtual Z rotations. The difference you can see is that in the digital analog case, the flux pulse needs to be adiabatic. In the digital case, it's faster. And this is because we need to control to stay in the computational subspace. This is possible for 2 qubits. It's possible with the fast flux pulse, but for more than 2 qubits simultaneously, this is not possible. So we need to be adiabatic in this case. So let me show how we realize the minimal implementation. So let's say we only have 2 qubits, which is then the Bell state preparation. Here you can see again our chip. We have the middle qubit, which is qubit 3 in this case, coupled to qubit 1 via the tunable coupler. And now we have 2 ways to implement the digital analog algorithm. The first one is the stepwise stack. Here we have the single qubit gates, and in the middle we have the analog evolution, and then again single qubit gates. As you can see, we have the adiabatic flux pulse there. And the other implementation is the bank duck, where we have the analog evolution on top. So we apply the single qubit gates on top of the evolution. We don't shut this down. We have this all the time on. The advantage of this is, in case we want to have more analog blocks, we don't always to turn off the interaction, turn it on again, turn it off again, turn it on, because this takes a lot of time. So there, a bank duck has an advantage that we just turn it on at one time. Okay, now let me introduce our results. First, for the stepwise duck scheme. On the left, you can see state tomography of the Bell state for the stepwise duck. And now we compare this to the digital case. You see that the fidelity of the digital case is better than the stepwise duck. This is expected because we only have 2 qubits. And for 2 qubits, as we need to use an adiabatic flux, for the stepwise duck, of course, the protocol is much longer. You see that the flux pulse in the stepwise duck case is 480 nanoseconds, and compared to the digital one, this is only 130 nanoseconds. So we would only expect an advantage for the stepwise duck protocol when we have 5 qubits, which leads to 4 qubit pairs. Yeah. So, and now let me come to the bank duck. There we have to meet some challenges because we apply the interaction and single qubit gates on top of the interaction. So challenge 1 is that during the state preparation, which you can see in the yellow box, we need to drive with an interacting frequency. But during state tomography afterwards, the interaction is turned off. So we have a different qubit frequency. And this can just be done in software. So this we can solve easily. We just need to drive with 2 different frequencies. This was an easy fix. Now let's come to challenge 2. Here, during the interaction, the frequency of one qubit depends on the state of the other qubit and vice versa. This is a little bit more complicated. You can see the level scheme there. In the non-interacting case, the 2 frequencies are just the same. But with the interaction on, we have different frequencies. And this is a problem because you see in the beginning we prepare a superposition state. So we are not in the ground state and not in the excited state. So there is no defined frequency. So we do a detuning error. And the tuning error consists of an amplitude error and a phase error. The amplitude error, we just don't solve. This will just be there. This will be larger for pi pulses than for pi half pulses, but it is there. But the phase error we can correct. And the solution is that we need to drive just with the mean frequency, and then we can correct for the phase error via virtual Z rotation, which you can see also in the yellow box. And single qubit phase rotation is in the analysis after the experiment. So this we can solve for. And we can also calculate this virtual Z rotation analytically, and we can sweep it in experiment. And here you can see a plot where we swept the virtual Z rotation versus the interaction time, where we need to have the flux on, and then we get to an optimal value. And this value we take then to do state tomography, and the result you can see on the left plot. There we did state tomography for the bank duck. And on the other plot, which you can see, we now have varied the single qubit gate duration. So of the single qubit gates we apply on top of the flux interaction. This we did for 2 different qubit pairs on our chip. The trend in the beginning for short single qubit gate durations is the same for both. So it has, at some point, it has a maximum. And that it goes down for short single qubit gates can be attributed to leakage. Then for higher single qubit gate durations, the main error source would be decoherence. And now the question is, why is it so different for the 2 different qubit pairs? And the reason for that is that for the gray part, qubit 1 has a much higher coherence than qubit 5. So this is also an indication that these decay can be attributed to decoherence. So qualitatively, we understand what is happening there in bank duck, and this is really important for our co-design approach. So the next step would now be, what happens for more than 2 qubits. Now we fundamentally understood what happens for 2 qubits, but now the interesting stuff comes when we go to more than 2 qubits. And for example, 3 qubits, we then have the real GHZ state, not the Bell state, but the real GHZ state. So let's focus on the 3 qubits we have. We have the middle qubit, qubit 3, and then 2 orthoqubits, qubit 1 and qubit 5, which are coupled via tunable couplers. And you can see the theory Hamiltonian, the interaction Hamiltonian only, there on the plot. So we have a coupling between the qubits. Now, in reality, this is just an approximation. We can also measure other terms which we don't want to have, actually. For example, although qubit 1 and qubit 5 are not directly coupled, there is a small, or there could be a small interaction between them. And we tuned the fluxes of the tunable couplers in the color plot to see what is the coupling between qubit 1 and qubit 5. And luckily, this is nearly 0, so this is fine. We're happy that there is no big coupling between them. But there could also be another indirect coupling, namely the coupling between the 3 qubits, qubit 1, 3, and 5, so 3-body coupling. And this you can see on the other color plot. In the worst case, the coupling is around 80 kilohertz, which does not sound so much, but it's around 7% of the wanted coupling in the darkest area. So this still needs to be figured out if this is a problem for our approach when we go to more than 2 qubits. Okay, with this, let me come to our conclusions. We did the first co-design experiments on an IQM 5-qubit QPU. And we explored the duck paradigm for the GHZ state generation. And you can see the algorithm again there. The advantage is that there we have a constant depth compared to the digital case where we have a longer depth. Then we generated the 2-qubit Bell state in digital stepwise duck and bank duck manner. And the pulse schemes you can see again there. For the digital and the stepwise duck for 2 qubits, it's just the same, except for the adiabaticity of the flux pulse. here you can see the fidelities we get. Of course, for 2 qubits, the fidelity is the best. For 2 qubits only, interesting stuff only comes later. So the outlook would be, of course, scaling to more qubits and see if we really have an advantage. And then we need to do an exact error budgeting. So what errors contribute more, which contribute less. And also, which is a good thing, we can use these tools we figured out here now for other co-design experiments. So in the future, there will also come different co-design experiments, and now we have a good basis to start with this. And with this, I thank you for your attention, and I'm happy to answer your questions.
Right, thanks. And now time for questions, please. Yep, they're at the back, please.
Yeah, thanks for the nice talk. So you mentioned that for the analog circuit, you have constant time. So is this, what is the origin of it? It's because you have this star structure that all qubits are coupled via the star. And could you comment of if you had like more complicated, larger circuit, what would then be like the scaling of the time with system size?
For the digital analog or what?
For the one with digital analog. Yeah.
There you can imagine that you do 2 qubit gates at the same time. So you just can scale them up doing them at the same time, so the algorithm does not become longer.
But for is it crucial for that you have this star structure that all the qubits are coupled via one coupler in the middle?
Yes,
so I mean that's
crucial.
not scalable, right? So my question is, okay, if I want to have GAZ state in whatever 10 qubits, so you would need to have like couple them differently, right? Would then that affect the time, the preparation time?
Yeah, because when you have the star type architecture, you have one analog block. And when you have another structure, you may have more analog blocks, so then the algorithm will become longer. Therefore, this is also an advantage of co-design, because we have a special chip and do a special algorithm on this. So this fits together then.
Yeah, thank you.
Right, more questions, please. There is another one. Yeah, sure.
Okay, I will use the opportunity to ask more. So now, okay, so with digital circuits, people are exploring a lot now parameterized circuits, like a VQE, where you would then train it to do some, possibly not unknown state. So did you think about it doing something similar with the analog circuits, that you would try to train them to prepare some state?
No, we didn't.
Thank you.
I don't think that you can train them, because this is just a system Hamiltonian you have. So, yeah, then you just can change the system. Yeah.
Well, there are some parameters still you can tweak,
yeah,
right?
Yeah, you can change the couplings, of course, yeah. Yeah, yeah.
We had a hackathon challenge that ended yesterday on digital analog VQE. So if you did not have the chance to participate in that one in the hackathon, then we'll be happy to share the results and how that was presented.
Right. Any more questions to Julia? If not, let's thank Julia. All right, and then we have one of the masterminds behind IQM's quantum computers, Johannes Heinso, talking about state-of-the-art readout and 2-qubit gates.
Thank you, Mikko, for a very kind introduction. My name is Johannes, and I'm here to present you the hard work done by the engineering team at ESPO, which is behind the sample Julia used and showed you. So I will basically tell you the story behind this sample, focusing on the 2-qubit gates on which we have a preprint on arXiv early this week about. So our goal really is to build also like using conventional digital components, a large qubit lattice with many qubits. So we really wanted to scale, and we want to solve the problems of the scaling early on immediately, not into walking to dead ends. So we have been working on how to make good gates and good readout in the same architecture with the compatible geometrical elements. And this talk really focuses on the story behind 2-qubit gates. I will tell you about 3 challenges and how we solve them, and in the end show the compatibility with the good readout. So I want to start by showing you optical false-colored micrograph of the same sample Andreas showed you in the morning. I have chosen one special unit cell, and you will later see why I exactly chose this one. It was also part of the discussion after his talk. But the 2-qubit gates here have a rather typical, well-known implementation. So the 2-qubit gates are implemented using the capacitive coupling mediated by these blue waveguides, or the sort of just elongated islands, with both yellow qubits coupled to. And it is not rare that such gate implementation reaches a lifetime limit. So one is really motivated to make these gates really fast because we are lifetime limited. So in order to improve the performance, you want them faster. And the speed limit is given by the coupling strength. And the fastest way to do a gate is to just diabatically switch the interaction on and off. You cannot go faster than J. And the off rate is then, in this case, given by how far do you detune the qubits. So you can evaluate the on-off ratio, which is if you pick some really optimistic numbers, it's maybe up to 100, but in many cases it's below 50. So the identity gate is actually really the elephant in a room. So good 2-qubit gates have been implemented many times, but this fact that you have this parasitic always-on coupling has been a little bit hushed under the carpet in many cases. So in case of flux qubits, the tunable coupler, which can really completely switch off the coupling, was implemented a long time ago. In transmon community, it was a little bit ignored for a while. Only team which really worked on these inductive tunable couplers was the team from Google. If you then just a year before IQM got started, there was this proposal from MIT about capacitive tunable coupler, which is also the path we chose because we believe that this will be less sensitive to the problems regarding flux crosstalk. Okay, so we solved the first problem. The next problem is about the size of the elements. I'm talking about the relative size of the qubit lattice and the size of the qubit. And if you make this lattice space small, you will struggle fitting the elements which each qubit needs. Each qubit needs a readout resonator, and the readout resonators based on coplanar waveguide resonators set you the lower bound on how small this lattice can be, as illustrated by the picture of the lattice from the ETH device. In addition, small lattices will have trouble with control selectivity, so one drive line will drive many qubits and next nearest neighbor crosstalk. And on the other hand, if you just make the lattice large to avoid these problems, to easily fit resonators without any crosstalk, you will actually make the 2-qubit gate interaction weak, because these couplers in between, the effective capacitance will be just diluted by the capacitance to the ground. It's a very practical problem, but it is really heavily illustrated by all of these implementations of the tunable couplers. The designs which are available in the literature, they all rely on the qubit-qubit capacitance implemented by direct capacitance between the center islands of the qubits. So this really will be challenging to make a lattice out of unless you have access to some advanced 3D technology. And you might still have problems such as control selectivity or next nearest neighbor crosstalk. So as Julie already showed you, here's a piece of our device. We do use tunable couplers, and the one shown in this picture more or less implements exactly the same circuit as proposed from MIT. We just make these conductors here much longer than it looks like in the lumped element circuit. There's of course there's also small capacitance here in series, and here we connect with an air bridge. Okay, you cannot see my mouse, I'm sorry. Okay, this qubit shape is perhaps also slightly unconventional. It is similar to the recent qubit designs from ETH, first introduced in Andersen et al. It has 6 ports we can tune individually, a small crosstalk between the drive port or control coupling ports. We can have a much more stronger coupling compared to the more conventional qubit designs, and we have validated that this is compatible with reasonable lifetime of the qubits. Here the histogram shows you statistics over 10 5-qubit devices where the median qubit T1 time was above 35 microseconds. Okay, and the third problem we want to solve is the frequency spacing problem. So due to the cost of the electronics and necessity that the readout resonator occupancy is really low, often the readout resonators are above qubit frequencies. And this conventional tunable coupler design has the tunable coupler idling point about 2 gigahertz above the qubit frequency. So during a 2-qubit gate, the tunable coupler would cross the readout resonator. During the gate, the tunable coupler is really far from the sweet spot, so this hurts the coherence also of the qubits due to the strong hybridization. And if you really push this to the speed limit, you notice that you will not be limited by the coherence, but actually by leakage to the F state of the coupler. And all of these 3 problems you can avoid if you change the sign of one of the coupling terms. This way you get the tunable coupler below the qubit frequency. So for comparison, I'm still showing the original circuit, but in the middle you see 2 circuits later proposed which solve the same problem. So the upper one by Zed et al. It has 2-island coupler, and the 2 qubits couple strongly to different islands of the coupler. And the lower one has a tunable coupler and first qubit coupling to different islands of the second qubit. We have chosen to have a on the right hand, you can see our circuit with gray indicating the effective capacitances. We have chosen that our qubits are single island qubits, so one of the islands are grounded, but the coupler has both islands floating. And it is still a novel circuit. It differs from the upper middle circuit because we explicitly implement the capacitance between the islands C and F, which we, according to our analysis, allows us to implement a stronger effective C1-2 and therefore a faster gate. Okay, and this circuit can be used in many ways to implement the gate. Here I want to walk you through the way how we do a gate using the circuit. So I'm going to walk you through the figure in the middle, where the horizontal axis is the coupler frequency and the vertical axis is the detuning between 2 qubits. Qubit frequency is given by the dashed orange lines, and the color represents the rate at which we collect the conditional phase. So this basically tells you how fast you can do a gate. So we want to park the qubit somewhere where the orange and blue, we want to park the coupler somewhere where the orange and blue meet. At this point we have 0 coupling. So we use the point marked by a dot close to the white dashed line, which indicates the staggering regime. So the qubits are parked more or less such that the detuning between them is really close to unharmonicity, but doesn't need to be there exactly. And from this point, we apply a flux path to the tunable coupler such that that on this map, on this landscape, we move across the black line, which indicates 25 nanosecond gate time. Okay, so the only thing we do to implement the gate is send a single flux pulse. We don't flux qubits, and the cost there is that we are a little bit more susceptible to the single qubit gate drive crosstalk, but we have other ways to mitigate that. But yeah, today it a little bit shows in the single qubit gate crosstalk. On the figure on the right, we can see experimentally obtained coupling strength as a function of coupler frequency. Which, from there, we can confirm that we do have this regime where the coupling strength changes sign, so we can completely shut off the coupling and reach coupling strength as high as 25 megahertz. So this is the configuration we are going to use. And I would like to further advertise these components, with what we call waveguide extenders, with waveguides on the islands of islands C and F. They have this advantage that they allow us to make this qubit unit cell large enough such that the other necessary components fit there and we can reduce crosstalk, while we still have reasonable coupling strength. The left figure shows you the coupling between the qubits and the center island on the left vertical axis, and on the right vertical axis there is the coupling between the qubits. And the x-axis is the distance between the qubits, and in a wide range we can get a strong coupling. So we could also change the size of the unit cell if necessary. It's not so fine-tuned for a single distance of qubits. So this is advantage one. We can make a large unit cell, and the second advantage is really a specific problem when you want to do a bigger device. So in a bigger device, you would have so many control lines accessing the center qubit that you need to make use of the flip chip technology. You would have a second piece of silicon and control lines accessing these qubits on the other chip. So in this diagram, the qubits are on a bottom chip and the control lines are on a top chip, represented by this black line, which represents the cross-section of a waveguide which is perpendicular to the plane of the figure. And let's imagine that this drive line is there to drive a third qubit, which is not shown in a figure. And on the lower plot, this R represents the relative Rabi rate when you would drive the relative rate between driving this qubit 3 and driving one of the qubits on a figure. And this basically quantifies the drive crosstalk you will encounter. And compared to these designs where these coupler extenders do not exist, this would correspond to the situation where this black drive line would be in the center of the top chip, just above the coupler. Compared to this situation, we can reduce the crosstalk by a factor of 10. Which is a significant improvement. And another thing we care about is this absolute value of this relative Rabi rate. We can see that we care more about driving the qubits, and next to the qubits, the relative Rabi rate is below 10%. So which is comparable to packaging crosstalk in the single-phase chips. And this crosstalk could be further improved by increasing the flip chip distance from 8 micrometers to something higher, or by adding some indium bumps, which were not part of this simulation, which would further shield from crosstalk. But but in this case, these coupler extenders are part of these waveguide extenders are part of the problem mitigation, because they do have lower crosstalk when crossing qubits and couplers. Okay, and how well does it perform? In interleaved randomized benchmarking, we can extract a gate error of 2 parts per thousand, so it's 99.8% fidelity. And in order to improve because this interleaved randomized benchmarking really doesn't look so trustworthy, because the two curves really overlap a lot. So in order to increase confidence that the gate really has so high fidelity, we have executed iterative interleaved randomized benchmarking, where we apply multiple C-phase gates, and this way the uncertainty in the fidelity estimate decreases by order of magnitude. And we compare it to a coherence-based error budget, and we find a very good agreement between. So in the lower right figure, we study the error rate as a function of gate length, theoretically, and the black line, which includes all the decay and dephasing sources, agrees well with the marker which represents the experimental data, which which tells that we understand our errors. But in order to achieve that, we really had to make the model rather sophisticated to distinguish carefully between dephasing originating from white noise and 1/f quasi-static noise, since one of them really dominates if you just measure T2 in a Ramsey, but it's actually somewhat cancelled out in the randomized benchmarking experiment. After careful analysis, we reached an agreement between expectations and observations. And I want to show you that this implementation is compatible with good readout. So standard way of doing qubit readout is to have readout resonators for each qubit, and they all couple to a single Purcell filter. But this such architecture does not protect you from accidentally probing not a single readout resonator, but all of them. So this is sort of a probe crosstalk. And also, if you really push this to be as fast as possible, you would make all the readout resonators as wide as possible. We start to interfere with each other, and you can compensate this in the design, but then you will become quite sensitive to small perturbations caused by the packaging and manufacturing non-reproducibility. So our QPU, the design features first the individual Purcell filters for each qubit, which can fit the unit cell, possible unit cell because of our large tunable couplers. So we have individual Purcell filters, but in addition we have what we call probe line resonator, indicated by blue. And so also the probe line forms a resonator, and this has two advantages. It enhances the coupling between the probe line and Purcell filters, which allows us to have wider Purcell filters, which will be in a more stable parameter regime. And also it works as an impedance transformer, making the Purcell filters less sensitive to the impedance of the wire bonds, for example. On the right, there is a transmission spectrum and single-shot signal distribution for two states of the qubit, from which we extract readout error below 1% for 100 nanosecond probe pulse length and integration time. This readout was achieved with the traveling wave parametric amplifier provided by Finnish National Research Center VTT, which had a gain above 10 dB and 1 dB compression point close to -100 dBm. So we believe that we have all the elements for a scalable lattice. So the one you see on the left is just Photoshop, but we have a real device in reach. I'm excited to show you these results in future, and these elements are compatible with 2 parts per 1,000 gate error and 1 part per 100 readout error. And they are lattice compatible. And here I'm highlighting some of a few experimentalists, Fabian Ante and Mikhailo, who are behind the experimental work, but the engineering is really a big collaboration between the design, fabrication, software, mechanical engineering, and theory team. So there's a lot of people who contributed to this work, and the readout-related the 2-qubit gate results are available in a preprint on arXiv. Thank you.
Right. Adrian, please.
Thank you for your talk, Johannes. I was wondering if distortions of the control pulse are a problem, and if so, how you correct and characterize them on the coupler.
Thank you. So the question is about the control pulses of the tunable coupler, so the flux pulses. And in this conventional gates, one has to be very careful both about long-term effects and short-term effects. And in this because the tunable coupler is parked very far, and it's in quite wide range of frequencies. The tunable coupler actually, the coupler is quite weak, so you don't need to be so precise, but you do care about the long-term effects adding up. So we do apply the standard method to this infinite impulse response filter to compensate for the parasitic capacitances, but we do not need to be so careful about the short-term effects, so we do not apply an FIR filter.
Thank you.
Right, more questions to Johannes. There, please.
Thank you, first of all, for this nice, insightful talk. I have a question about the nice coupler that you show. So you spoke that you have this two-island coupler, but what I see in this design, it looks like a single-island coupler or grounded coupler.
Yeah, your observation is correct. The design we show has a single island. The best results we have for the two-island coupler, and we will continue integrating the two-island coupler to our larger devices and hopefully share more in future.
And maybe like an after question after this, in one of the designs you showed a single line as a flux line to the grounded coupler. Do you also use it as an XYZ line, or do you just really use it as a Z line for this design?
The couplers only need the Z control. While in the characterization experiments we have, we do, it is nice to measure T1 and T2 using standard methods also for the coupler, and the couplers don't have a XY line or drive line for that. But due to the strong hybridization of the qubits, you can actually just, with a much lower Rabi rate, but you can drive a coupler using the qubit control line. So this is what we do for characterization, and it just results in order of magnitude lower Rabi rate, but that is sufficient for characterization experiments.
Okay, thanks.
Right, so let's thank Johannes for the nice talk.
So I just have now some organizational announcements to make. So we have now 3 exciting excursions coming up. This means we have a tour through Helsinki by Helsinki partners. We have an excursion to Bluefirst facilities. And that's actually pretty exciting because you're able to see not only their new system, or a sneak peek to their new system, KEYNOTE, but it's also that you're experiencing their own restaurant. Actually, that's a fact I didn't know. And lastly, you can visit IQM, and all 3 of them are pretty happy to host you. Now, for some organizational stuff, all excursions will last roughly 3 hours. They are all including food, so you don't need to worry about your dinner. The buses for the IQM on the Bluefirst tour, they'll leave at 18:20 upstairs, so you have like 10 minutes time to go upstairs and find the correct bus. There are people guiding you on the way and helping you to find the correct bus. You find, if you forgot which excursion you are, you find it on your badge. Might be that you're last minute registered for one of the tours, then you can still go there, at least for the Bluefirst one. For the Helsinki tour, we'd kindly ask you to stay down here, and we'll announce when the groups are leaving to that tour. And other than that, I'd like to thank you also, the session chairs of this afternoon, and also Vladimir Manucharyan for the nice keynote. We have a little present for you as well, so please stay around for a short time. And then I wish everyone a very nice evening. Enjoy the excursions. They will be pretty nice. And thanks for spending the whole day at SQA conference. Cheers.